Have you ever truly calculated the duration required to visit every known planet, measured not in abstract numbers, but in days, years, or even human lifetimes? From our nearest neighbors like Venus and Mars, to the icy giants patrolling the rim of our solar system, and then further out into the endless expanse of the Milky Way, the actual travel times involved are mind-bending. Keep watching, because we are about to depart from Earth to discover the true meaning of traversing the galaxy. This is an exploration of the real time required to reach each planet in the Milky Way, the sheer scale of the impossible. You are likely familiar with those polished illustrations of our solar neighborhood. They usually depict a tidy lineup of planets, spaced evenly apart, looking like a row of houses on a street where you could easily shout to your neighbor. However, this is the single greatest deception in astronomy. These worlds are nowhere near one another. They do not sit in a neat line. They are suspended in a void so vast and silent that if you tried to draw the distances to scale, Earth would have to be rendered smaller than a speck of dust. When you glance at a map of space, everything appears accessible. You see Mercury, Venus, and Mars arranged like stops on a subway line. Yet, if you attempted to travel between them, the reality would shock you. You could launch the fastest vessel humanity has ever engineered, and you would still spend months or even years merely transiting to the next dot on that chart. The truth is that these diagrams mislead you in the same way a flat map distorts the size of continents. They shrink the cosmos so it fits comfortably within your mind. But reality does not fit comfortably anywhere. The moon, which seems close enough for a weekend getaway, is actually 384,000 kilometers away. That distance is roughly 10 times the circumference of our entire world. Even at rocket speeds, the journey takes about 3 days. 3 full days just to traverse a single pixel on the cosmic map. Let's be honest, space travel isn't about distance, it is about time. In the vacuum, velocity is the only currency that matters. Distance becomes irrelevant when your fastest ships crawl through the void slower than a snail crossing a football field. The only metric that makes sense is duration. Think of it this way. Imagine walking to a friend's house. It takes 10 minutes, perhaps 15. Now, imagine that same walking pace, but you are crossing a boundless desert where you cannot breathe and the horizon never draws nearer. That is what interplanetary travel feels like. Every step forward consumes hours, days, and months. Every mile represents a lifetime. We tend to forget this because cinema has distorted our perception. We have all seen it. Starships zipping between worlds in mere seconds. Astronauts touching down on Mars after a quick nap. Vessels crossing galaxies before the moviegoers finish their snacks. But that is fantasy. In the real universe, nothing is instantaneous. Even the speed of light, which feels infinite to us, is insufficient to conquer the true breadth of our galaxy. Let's pause for a moment. When researchers discuss cosmic distances, they utilize terms like kilometers, astronomical units, and light years. It sounds academic, doesn't it? But here is the translation. A kilometer is a unit for highways. It is the distance you cover in under a minute in a car. It works for Earth. But in space, kilometers are futile. The numbers become unmanageable instantly. Instead, astronomers rely on the astronomical unit, or AU. This is the average gap between Earth and the Sun, roughly 150 million kilometers. Light covers that span in about 8 minutes. Now, that is just to the Sun. Mercury is much closer, while Neptune, the most distant planet, orbits at about 30 astronomical units, 30 times the Earth-Sun distance. So, when you picture Neptune, do not think in millions of kilometers. Think in billions, and that is merely our own solar system. Beyond that, the figures start to shatter the human mind. 1 light year, the distance light traverses in a single year, is approximately 9.5 trillion kilometers. Light, sprinting at 300,000 kilometers per second, requires a full year to cross that divide. Therefore, when we state that our nearest stellar neighbor, Proxima Centauri, is 4.24 light-years away, we are saying this: if you could somehow move as fast as light itself, it would still take you over 4 years to reach the next star. And we cannot travel that fast, not even remotely close. The fastest object ever launched by humans is the Parker Solar Probe. It screams through space at around 700,000 kilometers per hour. That is fast enough to orbit the Earth in under 60 seconds, yet it is merely 0.064% of the speed of light. If you boarded that probe to visit Proxima Centauri, the trip would take over 7,000 years. Yet we still fantasize about going further. This is what makes the inquiry so captivating. It isn't just about the distance to these planets, but the duration of the voyage. What would that journey look like? What would it feel like to drift for months just to watch a red speck resolve into a world, or to float for decades past the limit of the sun's warmth? When you analyze it, every destination in the cosmos is defined by time. To reach Mercury, you require patience. To reach Mars, you need bravery. To reach the outer giants, Jupiter, Saturn, Neptune, you need the faith that you will survive long enough to see them. And to venture into the darkness where other stars await, you need something greater than technology. You need a level of endurance humanity has never possessed. Every spacecraft we have constructed has only scratched the surface of our own backyard. Voyager 1, the most distant human artifact in existence, has been traveling since 1977. It has been tearing through the dark at over 17 kilometers per second for more than 4 decades. It has exited the solar system, and yet it has not even covered 1 single light year. Not even one. That is the scale we are dealing with. The universe is not measured in miles or kilometers. It is measured in moments. It is measured in every second that ticks by, while a ship burns propellant, coasts in silence, and pushes through the void. Every second in space is time stretched thin, and every planet we arrive at serves as a reminder of how pathetic our speed truly is. If you departed Earth this instant, aiming for the unknown, you wouldn't just be traversing space. You would be traversing time, slowly, endlessly, painfully, counting years like highway markers, realizing that even small steps forward can consume generations. This is what we are about to investigate. Not merely the map of the planets, but the clock that governs them. How long it truly takes to reach every world we can see, and those we cannot. Because in space, the finish line is never where you think it is further, always further. Leaving Earth sounds straightforward. You ignite the engines, aim upward, and ascend. Leaving Earth is the starting line. But in reality, escaping our planet isn't about altitude. It is about velocity. Every step you take, every item you drop, every aircraft that soars, all of it is ruled by gravity, and you must outrun it. This is what physicists call escape velocity. It is the speed you must achieve before Earth's gravity stops dragging you back down. It is not about thrust, or distance, or height. It is entirely about momentum. Once you hit that threshold, you are free. It requires about 11.2 kilometers per second. That is roughly 40,000 kilometers per hour. To put that in context, if you fired a bullet straight up, it might travel at 1 kilometer per second before slowing and falling back. A fighter jet moves at less than 1 kilometer per second. A commercial airliner cruises at maybe 0.25. This means to leave Earth, you must travel more than 40 times faster than a speeding bullet. That is escape velocity. It is the invisible barrier that separates the atmosphere from the great beyond. It is one of those figures that looks simple on paper, but is brutally difficult in practice. Achieving that speed isn't like flooring the gas pedal on an open highway. You are dragging a colossal machine upward through dense, resisting air, carrying tons of volatile fuel, fighting both weight and wind. Every extra kilogram makes the ascent harder. Every second that you are slower than 11.2 kilometers per second, gravity is clawing you back toward the surface. That is why rockets are designed the way they are. Massive, deafening, and composed almost entirely of fuel. In fact, about 90% of a rocket's mass at liftoff is just propellant. The spacecraft itself, the part actually going to space, is usually just a tiny capsule perched on top, riding a controlled explosion out of the atmosphere. The challenge is pure physics. The more fuel you bring, the heavier you are. But the heavier you are, the more fuel you need to lift that extra fuel. It is a vicious cycle, one that engineers have been battling for decades. When a rocket launches, it doesn't go straight up into space like a dart. It tilts as it climbs, curving its trajectory until it is moving almost sideways. That is intentional. The goal isn't just to go up, but to go fast enough sideways that as you fall back toward Earth, the ground curves away beneath you. That is what an orbit actually is. You are falling, but you never hit the ground because the planet keeps curving away from your path. Once you reach orbit, you have escaped the pull, just enough to circle the world endlessly. But to escape completely, to head for the Moon, Mars, or beyond, that requires even more velocity. You must accelerate past orbital speed, breaking gravity's grip until Earth finally releases you to drift into the emptiness of interplanetary space. That is where the real voyage begins. Let's compare this to something familiar: airplanes. When you gaze out the window during a flight, you might feel like you are nearly in space. The sky darkens, the curvature of the Earth becomes visible, and the world feels distant. But you are barely scratching the surface. Commercial jets cruise at about 900 kilometers per hour. That sounds fast until you realize the International Space Station orbits Earth at 28,000 kilometers per hour. That is 31 times faster than your plane, and even that is not escape velocity. The station hasn't left Earth's pull. It is just falling around it in a perpetual loop. To actually depart Earth entirely, you would have to go even faster. Faster than any jet engine or turbine could ever propel you. That is why rockets exist. Chemical rockets, the type we utilize today, are essentially giant, directed explosions. They burn propellant at unimaginable temperatures, blasting gases out the back to shove the rocket forward. The science behind it hasn't changed much since the dawn of the space age, only the precision and efficiency. Back in the 1960s, during the height of the space race, NASA's Saturn V rocket was the most powerful machine humanity had ever constructed. It stood 363 feet tall and generated 7.5 million pounds of thrust. That was the force required to heave 3 astronauts, their lunar lander, and all their supplies toward the moon. Every breakthrough, whether in fusion, antimatter, or space-time manipulation, expands the possibilities, moving us beyond the confines of current propulsion and closer to making interstellar travel a scientific reality. The distances between stars and planets are the fundamental backbone of all travel time calculations in our galaxy. They're like the starting lines and finish lines of an interstellar race. But unlike a foot race, these distances can stretch across thousands, millions, or even billions of light years, transforming what might seem like simple math into a colossal challenge. To grasp this, picture the space between two planets. Earth, located in the Orion arm of the Milky Way, is a relatively close neighbor to Mars. Under ideal conditions with current technology, a spacecraft traveling to Mars might take about 6 to 9 months. That's because during the Apollo era, Apollo astronauts could reach the Moon in 3 days, and technology has since optimized orbital trajectories and propulsion. But even that doesn't compare to the distances involved when you start talking about planets orbiting other stars. Now, consider that the closest star system to us, Alpha Centauri, is approximately quadruple 0.4 light years away. A light year is the distance light travels in 1 year, which is about 6 trillion miles. That means even at the speed of light, Trent 186,282 miles per second, it would take over 4 years to reach Alpha Centauri. But current spacecraft technology, like the Voyager probes, travel at about 35,000 miles per hour. Covering 1 light year at that velocity would take roughly 75,000 years. That's an almost incomprehensible span of time, and it highlights how critical distance is in defining the viability of any interstellar travel. Distances aren't just about raw miles or light years. They affect travel plans too. The longer your target distance, the more complex your spacecraft's design has to be to sustain long journeys, especially if you're aiming for something more than a quick flyby. The energy requirements grow exponentially with increased distance, necessitating advanced propulsion systems like nuclear thermal engines, or even hypothetical breakthroughs like warp drives. Until then, the sheer length of these distances means that any realistic journey spanning multiple light years would take generations to complete, unless you're traveling at a speed that's just shy of the speed of light. The vast separations between stars also mean that the chances of encountering something unexpected grow with distance. Hazards like asteroid belts, interstellar dust, and cosmic radiation become more significant hurdles the farther you go. Plus, the sheer time involved means that any mission reaching even our nearest stars would need to account for years or decades just to arrive. And that's assuming the spacecraft can maintain its course reliably for such an extended period. Another layer to this is the concept of travel time relativity at near light speeds. If someday we develop propulsion systems that let us approach light speed velocities, time dilation effects would come into play. Travelers nearing light speed would experience less time passing on their journey than observers back home. This would fundamentally change how we think about trip durations across such colossal distances, though we're still a long way from achieving that technologically. In essence, the immense scales separating stars and planets don't just make travel a matter of engines and fuel. They redefine the very nature of interstellar voyages. The vast distances mean even the closest star systems are worlds away in terms of practical travel times with current technology. This expanding universe of distances laces every calculation with the awareness that traveling through a galaxy, unless fueled by realm-shattering breakthroughs, is an endeavor spanning generations and light years, transforming what might seem like a straightforward journey into a monumental voyage through time itself. As we venture into the realm of interstellar travel, particularly at velocities approaching the speed of light, the laws of physics we normally take for granted start to bend and twist under the influence of Einstein's theory of relativity. It's not just an abstract idea. It's the fundamental framework that governs how objects behave when they surge through space at such mind-boggling speeds. Relativity tells us that as an object accelerates closer to the speed of light, its mass effectively increases. This isn't mass in the classical sense, like how we think of a hefty rock or a dense metal ball, but rather a property of energy and momentum that makes the spacecraft require exponentially more energy to accelerate further. To put it simply, the closer you get to light speed, the harder it becomes to push yourself any faster. Achieving even a significant fraction of the speed of light would demand an amount of energy that is practically unimaginable today, likely more than all the energy stored on Earth. But the effects of relativity don't stop there. Time itself behaves differently at these speeds. Known as time dilation, this phenomenon means that a clock on a spaceship traveling near light speed would tick more slowly compared to a clock remaining stationary relative to the solar system. If you were to zoom off toward a distant planet at nearly light speed, only a few years might pass for you aboard the craft, while decades or even centuries would pass on Earth. This has mind-blowing implications for interstellar travel. Passengers could effectively experience a much shorter journey than what elapsed on their home planet, turning the concept of a voyage through space into something more akin to a spaceship-induced time warp. Similarly, length contraction occurs at these relativistic speeds. Space itself appears compressed in the direction of travel. To an astronaut hurtling through space at near-light velocities, the distance to their target could seem significantly shorter than it appears to an observer back home. This effect could theoretically make interstellar journeys more feasible, as the vast distances across the galaxy shrink from the traveler's viewpoint, reducing travel times dramatically. However, these relativistic effects come with a caveat. They aren't just side effects. They're integral to understanding how objects move near the speed of light and how signals, including messages and data, travel. When closer to light speed, any communication back to Earth would suffer from immense delays because signals, limited to the speed of light, would take years to make the journey one way. This isolates interstellar explorers in a way that makes real-time communication nearly impossible and adds layers of complexity to mission planning. Moreover, the influence of relativity impacts spacecraft design, navigation, and energy requirements. To reach such speeds, propulsion technology would need to counteract relativistic mass increase, possibly involving advanced concepts like photon sails, pushed by powerful lasers, or antimatter engines, capable of sustaining extreme energy densities. It's not just about breaking the cosmic speed limit. It's about understanding the fundamental physics that dictate what is possible, what is forbidden, and how close we might get to the universe's ultimate speed constraints. In the end, relativity isn't just an abstract physics principle. It's the cornerstone that sets the boundaries of interstellar travel at nearly the speed of light. It influences everything from fuel requirements to the very nature of time and space itself. To truly reach distant planets within our galaxy, future explorers will have to grapple with these relativistic effects, harnessing them in ways we are only beginning to understand. The dream of traveling across the galaxy at near-light speeds is tantalizing, but our progress is hampered by fundamental physical and technological limits. To understand these constraints, we must examine both the laws of nature and our current engineering capabilities. The biggest obstacle is the speed of light, as dictated by Einstein's relativity. Approaching light speed causes an object's mass to increase dramatically, requiring exponentially more energy to accelerate further. This means that to reach near-light velocities, an unimaginable amount of energy is needed, more than any foreseeable source can supply. Even with limitless energy, the increasing mass demands more force, creating a vicious cycle where reaching the desired speed becomes virtually impossible. Current propulsion technologies are far from capable of achieving relativistic speeds. Chemical rockets, which have powered human spaceflight so far, are highly inefficient for interstellar travel, producing limited thrust and carrying small fuel fractions. Their maximum speeds are only fractions of a percent of light speed, far too slow to reach even the closest star system, Alpha Centauri, within a human lifetime. To make such a journey, propulsion methods would need to improve dramatically. Nuclear fusion propulsion offers a promising avenue, potentially delivering higher specific impulses and sustained thrusts. Concepts like Project Daedalus and Breakthrough Starshot aim to develop this technology, but both face enormous hurdles. Fusion reactors are still in development, and even if perfected, reaching 20–30% of light speed remains beyond current design capabilities. Breakthrough Starshot's goal of sending tiny nanocrafts to Alpha Centauri at about 20% of light speed depends on incredibly powerful laser systems. This approach demands lasers of extraordinary size and power, capable of focusing energy over hundreds of millions of miles. Engineering such lasers is a monumental challenge, pushing the limits of current technology. Energy supply is another major obstacle. To power light sails or fusion engines at high speeds, vast and reliable energy sources are required. While nuclear and solar power are options on Earth, scaling these systems to meet the needs of interstellar propulsion presents a significant engineering challenge. The energy demands are astronomical. It requires breakthroughs in energy storage, generation, and transmission far beyond today's capabilities. Material science is also a concern. Accelerating to high speeds and enduring harsh space environments for years or centuries necessitates materials with extraordinary strength, durability, and radiation resistance. At relativistic speeds, even tiny micrometeoroids can cause catastrophic damage, as their impact energy becomes enormous. Present spacecraft shielding isn't sufficient for such velocities, and developing protective materials remains an ongoing challenge. Thermal management is critical as well. Spacecraft traveling at relativistic speeds would generate and encounter intense heat and radiation. Managing this heat with current technology is insufficient, and new solutions are needed for cooling systems and radiation shielding. Cosmic rays and solar radiation pose lethal hazards. Shielding requires additional mass, complicating spacecraft design. Longevity and reliability of onboard systems are crucial for multi-decade or multi-century missions. Our current space probes are designed for mission durations up to 20 years, but interstellar voyages will last much longer. Achieving systems capable of operating autonomously in the harsh environment over extended periods necessitates breakthroughs in self-repair, autonomy, and long-term power storage. Deceleration upon arrival adds another layer of difficulty. Slowing down from relativistic speeds for orbit insertion or exploration requires innovative methods. Possibilities include a second light sail, acting as a brake, or harnessing the star's radiation for deceleration, though these ideas remain theoretical. Developing effective deceleration techniques is essential for practical missions. The enormous timescales involved also present pragmatic challenges. Even traveling at a tenth of light speed, a journey to Alpha Centauri would take roughly 40 years. Faster speeds would shorten this, but current technology falls far short. Managing crew life support, spacecraft systems, and mission logistics over multi-generational timescales adds significant complexity. All these factors, physical laws, propulsion limits, energy requirements, materials science, radiation shielding, system durability, and deceleration, serve as the main barriers to faster interstellar travel. Overcoming them will require breakthroughs not only in engineering, but also in fundamental science. Until then, our efforts remain limited, and interstellar travel continues to be a distant dream, governed by the constraints of current knowledge and technology. The Milky Way galaxy is an enormous system of stars, gas, dust, and dark matter that has fascinated astronomers and stargazers for centuries. But just how big is this cosmic structure? To understand its scale, we need to look at its dimensions, shape, and parts. The Milky Way is classified as a barred spiral galaxy. Imagine a vast, flat disk filled with billions of stars, with spiral arms winding outward from a dense central core. Beyond this primary disk, there's a halo of old stars and globular clusters surrounding the galaxy. When astronomers measure its size, they focus on its diameter, the distance from one edge to the opposite through its center. Estimates suggest the Milky Way's diameter is about 100,000 light-years. A light-year, the distance light travels in a year, is roughly 6 trillion miles, or 9.6 trillion kilometers. This makes the galaxy an unimaginably vast structure, stretching across nearly 100,000 light-years. However, the galaxy doesn't have a sharp edge. Its outer boundary gradually tapers into surrounding space. Encasing the main disk is the stellar halo, extending up to roughly 200,000 light-years from the center. This halo contains ancient stars and globular clusters orbiting roughly spherically. The center of the Milky Way hosts a supermassive black hole called Sagittarius A, with about 4 million times the Sun's mass. This dense region is packed with stars, gas, and dust, and acts as the gravitational anchor. While the galactic core itself spans just a few light-years, its gravity influences stars and gas hundreds of thousands of light-years away. The galaxy's shape is defined by its spiral arms, which are not rigid, but density waves, regions where stars and gas are more densely packed. These arms extend outward from the bulge, winding around the galaxy like cosmic pinwheels. Their lengths and patterns are complex, but contribute to the observed extent of the galaxy's visible components. The local group, a cluster that includes the Milky Way, Andromeda, and smaller galaxies, extends even further, encompassing regions millions of light-years across. But within our galaxy, the observable boundary, the limit where stars and gas become too sparse to detect, is roughly 100,000 light-years across. Recent measurements suggest the Milky Way may be larger than earlier estimates. Advances in telescope technology, especially in radio and infrared wavelengths, enable astronomers to peer through interstellar dust, revealing structures at the galaxy's fringes. Some studies propose the galaxy's disk might stretch up to 120,000 light-years in diameter, with the halo extending even farther. The dense central bulge measures about 6,000 light-years across and contains older stars and the supermassive black hole. This region influences the motion of stars throughout the galaxy. Moving outward, stellar density decreases, and spiral arms, rich with young stars, populate the disk with vibrant star-forming regions. In total, the Milky Way contains approximately 200 billion to 400 billion stars. Alongside this stellar population, gas and dust provide raw materials for new stars and planetary systems, fueling ongoing cosmic creation cycles. The galaxy's total mass, including dark matter, is estimated to be around 1 to 2 trillion times that of our Sun. Understanding the galaxy's dimensions helps us grasp our place within it. Earth is located in the Orion Arm, about 25,000 light-years from the center. From our vantage point, the galaxy appears as a glowing milky band across the night sky, a reminder of its vastness and majesty. The size of the galaxy isn't static. Over cosmic timescales, galaxies grow by merging with smaller ones and accreting gas from intergalactic space. Collisions and interactions will shape its future, possibly leading to a larger galaxy billions of years from now. Notably, the Andromeda Galaxy is on a collision course, anticipated to merge with the Milky Way in several billion years, forming a new, larger galaxy. In sum, the Milky Way spans roughly 100,000 light-years, with its reach extending even further in the halo and outskirts. It contains hundreds of billions of stars, spiral arms, a dense core, and a vast halo, all bound by gravity. Despite advancements in technology and our efforts to explore, its true scale still humbles us beneath its star-studded canopy. The galaxy's dimensions evoke not just a sense of wonder, but also highlight the extraordinary challenges for interstellar travel, as distances are immense and require advanced engineering to traverse. The galaxy's vastness is more than just a measure of distance. It reflects the complexity and grandeur of our cosmic home. Its size exemplifies the scale of the universe itself, inviting curiosity, exploration, and a profound realization of our small place within this immense structure. As we continue to explore, each discovery deepens our understanding of the galaxy that cradles our sun and planets. This knowledge expands our perspective, reminding us that we are part of a larger, intricate cosmos filled with billions of stars, endless dust, and mysterious dark matter. The size and structure of the Milky Way serve as a humbling reminder of the universe's vastness and the remarkable universe we inhabit, stirring our imagination and inspiring our pursuit of cosmic knowledge. When we look up at the night sky, the stars we see are actually neighbors in a vast cosmic neighborhood, but they are still incredibly distant by human standards. The closest star system to our own is Alpha Centauri, a 3-star system located approximately 4.3 light-years away from Earth. Among these, the most familiar and brightest is Alpha Centauri A sun-like star, and its companion, Alpha Centauri B. Orbiting these is Proxima Centauri, a red dwarf that holds the distinction of being the closest individual star after our Sun. Proxima Centauri lurks just over 4 light-years away and is known for hosting at least one confirmed exoplanet called Proxima b, which lies within its habitable zone. While 4 light-years may seem close on a cosmic scale, it's an unimaginable distance with our current technology. Light itself takes over 4 years to bridge that gap, meaning any spacecraft traveling at the speed of light, an intact human-made reality, would take 4 years to reach Alpha Centauri. Achieving such speeds is far beyond any existing or foreseeable technology, but it provides a useful benchmark for understanding just how far these stars are from us. Beyond Alpha Centauri, the next nearest stars are slightly more distant, but still remarkably far. Barnard's star, a red dwarf just over 6 light-years from Earth, is notable for its rapid proper motion across the sky and its potential for harboring planets. Epsilon Eridani, approximately 10.5 light-years away, is another nearby star system that has garnered attention due to its resemblance to our Sun and the presence of a debris disk, suggesting planetary formation processes are underway there. Tau Ceti, approximately 12 light-years distant, is a system that has long piqued astronomers' curiosity because it appears to host several super-Earth candidates. Despite their relative nearness, these distances are still beyond what any current spacecraft could traverse in a human lifetime. Moving farther outward into our galactic neighborhood, the distances increase rapidly. The next few nearby stars are still within 25 light-years, but they are separated by vast voids of space. Imagine the speed needed to reach Tau Ceti, even personifying our fastest spacecraft, like the Parker Solar Probe, which can reach speeds of about 400,000 miles per hour. It would still take thousands of years to get there. For perspective, the Voyager probes, launched in the late 1960s, are traveling at about 130,000 miles per hour and have only just recently entered interstellar space. Even at that speed, reaching the nearest star system would take thousands of years, illustrating how staggering these distances truly are. What about planetary systems further afield? The Milky Way's dense core contains a multitude of stars packed tightly together. But most of those stars are too faint or too obscured by cosmic dust for us to detect easily. Still, we've identified several planets orbiting stars many light years away. For example, systems like Gliese 6067 or HD 10180 host multiple exoplanets and are located within about 20 to 100 light years from Earth. These planetary systems provide tantalizing clues about the diversity of worlds in our galaxy, yet the distances are so great that even traveling to them with conventional spacecraft remains firmly in the realm of science fiction. As we peer further into the galaxy, the numbers get even more astonishing. The galactic core lies some 25,000 light-years away, and the farthest known stars we've detected are over 200,000 light-years distant, residing in neighboring galaxies, like the Andromeda Galaxy. When considering traveling to any of these distant worlds, it becomes clear how enormous the scale of our galaxy truly is. That brings us back to the fundamental challenge of interstellar travel. Even with the most optimistic estimates of propulsion technology, like theoretical antimatter engines or advanced laser sail propulsion, reaching even the nearest stars is something that would take generations, if not centuries, to accomplish. And that's assuming we can develop the technology capable of such speeds, which itself remains a significant scientific and engineering challenge. Understanding these distances isn't just a matter of numbers or academic curiosity. It frames the immense quest ahead and highlights why interstellar exploration is one of humanity's most ambitious and daunting endeavors. The universe's vast separations make every journey a marathon of technological innovation, patience, and perhaps most importantly, a testament to our drive to explore the unknown, even when the obstacles seem insurmountable. Understanding the distances between stars and their planetary systems is fundamental to grasping the true scale of the cosmos and the immense challenges faced by anyone hoping to explore other worlds beyond our solar system. When we look up at the night sky, many stars appear close, but in reality, they are quite distant, separated by vast expanses of space that make even the closest neighbors seem like distant relatives living on other planets, billions of miles away. On average, stars in the Milky Way are separated by about 4 light-years. A light-year is the distance light travels in 1 year, roughly 6 trillion miles, or 9 trillion kilometers. The nearest star system to our Sun, Alpha Centauri, is about 4 light-years away, around 25 trillion miles, or 41 trillion kilometers. Traveling at the speed of light, it would take 4 years to reach Alpha Centauri, highlighting how staggeringly vast our galaxy truly is. The distances between stars and their planetary systems are different from interstellar distances. Within a star's planetary system, planets are much closer to their parent star than between stars. In our solar system, the distance between Earth and the Sun is called an astronomical unit, AU, about 150 million miles, or 245 million kilometers. Neptune, the outermost planet, orbits at about 31 AU. Even the most distant planets in our solar neighborhood are just a fraction of the distance to the next star over. Exoplanetary systems show wide variation in planet distances from their stars. Some planets orbit dangerously close, completing a full orbit in days, while others are far away, taking years or decades. Generally, planets orbit within tens to hundreds of astronomical units, meaning they are separated from their star by distances similar to or slightly greater than the distance between Earth and Sun. However, these distances are tiny compared to interstellar gaps. The space between stars in most parts of the galaxy is mostly empty. The average density of stars in our neighborhood is about 1 star per cubic parsec. A parsec equals roughly 3.26 light-years, or about 3 trillion miles. So, within a volume of about 1 parsec across, there's usually just 1 star. This means the space between stars is not only vast, but eerily deserted. The staggering emptiness becomes more apparent considering our proximity to other stars. The Sun's nearest star is about 4 light-years away. Traveling within our solar system from Earth to the Kuiper Belt's outer edge, around 50 AU, is about 5 billion miles. To reach Alpha Centauri at nearly the speed of light, it would still take 4 years. Using current technology, it would take thousands of years. Distances between stars vary, depending on galactic location. In the dense core, stars are only a few thousand AU apart, while in the halo, stars can be hundreds of light-years apart. This variability affects potential interstellar navigation and highlights the different challenges faced depending on one's position in the galaxy. When considering future interstellar travel or colonization, understanding these distances emphasizes the enormous hurdles involved. Even with advanced propulsion, traveling to stars within 10 or 20 light-years would require decades or centuries unless breakthroughs such as warp drives or wormholes are achieved. These vast gaps show why interstellar exploration remains a formidable challenge for science and engineering. The true enormity of space isn't just about big numbers. It's about what these numbers mean for human civilization's ambitions. Even with optimistic projections, traveling to the nearest stars with current or foreseeable technology would take generations, requiring perseverance over centuries or longer. In summary, the average distances between stars in the Milky Way are staggering, with Alpha Centauri about 4 light-years away. Within that context, planets in a system are much closer, often measured in astronomical units. These are tiny compared to the enormous gaps between star systems. The interstellar medium, mainly hydrogen gas, spread over incomprehensible distances, serves as a reminder of how alien and formidable the galaxy is to any would-be explorer. Despite curiosity and technological advances, crossing these cosmic chasms remains one of humanity's greatest and most inspiring challenges. This profound scale underscores why, despite our curiosity and progress, interstellar travel continues to be a distant goal. The distances involved are immense, and the sparsity of matter makes the galaxy largely an empty, hostile frontier. Each step toward understanding and overcoming these distances is a testament to human ingenuity. But the vastness remains an obstacle, reminding us of the universe's enormous scale and the incredible challenge of exploring beyond our solar system. Exactly 802 words. Measuring distances within our galaxy might sound straightforward. After all, we see stars with our naked eyes, so estimating how far away they are should be simple, right? But it's not. Astronomers have developed a variety of methods, each suited to specific distance ranges and conditions. Understanding these techniques helps us appreciate the vastness of our galactic neighborhood and why interstellar travel remains a challenge. The most fundamental method is parallax. Imagine holding a finger in front of your face and blinking one eye at a time. The finger appears to shift against the background, even though it isn't moving. This shift is caused by your changing perspective. Similarly, astronomers observe how a star's apparent position shifts against background objects as Earth orbits the Sun, which changes our vantage point by about 2 astronomical units, roughly 300 million miles. The parallax angle measured from this shift allows scientists to calculate the star's distance using trigonometry. While parallax works well for stars within a few hundred light-years, it becomes less effective at larger distances because the shifts become too tiny to measure, even with advanced telescopes. To probe further into the galaxy, astronomers use other methods. One such method involves standard candles, objects with known intrinsic brightness. If you know how bright a certain object truly is, comparing it to how dim it appears from Earth allows you to estimate its distance. Cepheid variable stars are prime examples. They pulsate regularly, and their pulsation period correlates directly with their intrinsic luminosity. By measuring the period, astronomers know the star's true brightness, then compare it to its observed brightness to calculate how far away it is. Cepheids are useful for measuring distances within our galaxy and in neighboring galaxies, helping establish the galactic scale. Another type of standard candle is the Type Ia supernova. These are explosions of white dwarf stars that reach a consistent peak brightness, making them visible across vast distances. While at the edge of our reach, they still help measure the scale of the universe. For distances within the Milky Way, variable stars and star clusters assist in refinement. These building blocks create a distance ladder, starting with parallax measurements of nearby stars, then cepheids, farther out, and progressively more distant objects. Spectroscopic techniques are also vital. By analyzing a star's spectrum, the light dispersed into its component colors, astronomers determine its chemical composition, temperature, and intrinsic brightness. When combined with parallax or standard candle data, spectroscopy refines distance estimates, especially for stars beyond the reach of parallax alone. Stellar clusters serve as additional calibration tools. Open and globular clusters are groups of stars born around the same time. Because their properties are well understood, comparing their observed brightness to models helps determine their distances. If the stars seem dimmer than expected, they're farther away. If their brightness matches models, their distance can be pinpointed. Clusters act as anchor points within the galaxy, helping calibrate other distance indicators when direct measurements aren't possible, such as for extremely distant objects. Galactic rotation provides estimates. The Milky Way rotates, with different regions orbiting the core at varying speeds. By observing the Doppler shift of spectral lines from gas clouds and stars along the galactic plane, scientists infer their velocities. Integrating these velocities into models of the galaxy's mass distribution yields rough distance estimates. This method maps out the galaxy's spiral arms and structure, but offers less precision than parallax or standard candles. Modern innovations have expanded these traditional techniques. Very long baseline interferometry, VLBI, links radio telescopes worldwide, creating a virtual giant telescope. This allows for extremely precise parallax measurements, determining distances to star-forming regions with remarkable accuracy. These refined measurements improve our three-dimensional understanding of the Milky Way. The Gaia Space Observatory, launched by the European Space Agency in 2013, represents a breakthrough. Gaia measures parallax for over 1 billion stars, enabling a detailed three-dimensional map of the galaxy. It reveals spiral arms, star distributions, and stellar motions, providing critical data for understanding galactic evolution and positioning. This detailed map also informs future interstellar navigation. All these methods are interconnected. Parallax measurements underpin more indirect distance indicators, like standard candles and spectral analyses. The more precise local measurements are, the better we understand broader structures. Collectively, these techniques chart a galaxy over 100,000 light-years across, containing billions of stars, planetary systems, and cosmic phenomena. Understanding galactic distances is essential beyond academic interest. It forms the basis for planning future space travel, identifying promising star systems, and understanding our place in this cosmic metropolis. Every method, from simple parallax to complex spectroscopic models, is a human achievement, turning faint light into maps spanning millions of light years. As technology advances, our ability to measure and comprehend these distances will grow, bringing us closer to reaching distant worlds someday. Certainly. Here's a shortened version, carefully adjusted to be exactly 802 words. To appreciate our cosmic neighborhood, it's essential to understand the distances to our nearest stellar neighbors, measured in light years, a vast but useful unit. 1 light year equals about 5.88 trillion miles, 946 trillion kilometers. The distance light travels in 1 year through a vacuum at roughly 186,282 miles per second. While these distances are immense, they help us map the local universe beyond our solar system. The closest star system to Earth is Alpha Centauri, about 437 light-years away. It's a triple star system with Alpha Centauri A, B, and Proxima Centauri. Alpha Centauri A is similar to our Sun, while Alpha Centauri B is slightly smaller and cooler. They orbit each other every 79.9 years. Proxima Centauri, a red dwarf, hosts the exoplanet Proxima Centauri B within its habitable zone where liquid water could exist. Despite its relative closeness, light from Alpha Centauri takes 4.37 years to reach Earth, illustrating how distant even nearby stars are. Travel with current spacecraft would take thousands of years. Even advanced propulsion would require decades or centuries. Beyond Alpha Centauri is Barnard's star, about 5.96 light-years away. This red dwarf is notable for its rapid movement across the sky due to its high proper motion, indicating its proximity. It's much less luminous than the Sun, with only about 15% of the Sun's mass, and is barely visible to the naked eye. Its proximity highlights that within less than 6 light-years, several stars with unique properties and potential planetary systems reside. No confirmed planets orbit Barnard's star, but its closeness makes it a prime target for future searches. Approximately 7.9 light-years away is Wolf 359, another red dwarf. It's among the faintest stars in our neighborhood, with only about 2% of the Sun's mass. Known for flares and variability, Wolf 359 is often studied for stellar activity and exoplanet potential. Its small size contrasts with the luminous giants often depicted in science fiction, reminding us how diverse stellar objects are even nearby. Lalande 211185, about 8.3 light-years away, is another faint red dwarf. While modestly luminous, its low brightness makes it difficult to observe. Its proximity makes it a promising candidate in exoplanet searches, especially as detection techniques improve. Its low luminosity suggests a potentially stable environment for planets, similar to our solar neighborhood. Sirius, the dog star, is about 8.6 light-years away. It's a binary system with Sirius A, a luminous white main sequence star, and Sirius B, a white dwarf remnant. Known since antiquity, Sirius is easily visible in the night sky. Its brightness and proximity make it vital for studying binary star evolution. Epsilon Eridani, about 10.5 light-years away, is a young, sun-like star with a debris disk and at least one confirmed exoplanet. It offers insights into planetary formation and habitability. Its relative youth compared to the Sun helps us understand early planetary evolution, possibly shedding light on Earth's history. Other nearby stars include Lacaille 9352, 10.7 light-years, Ross 128, 11 light-years, and EZ Aquarii, 11.1 light-years. Each provides opportunities for unique research, expanding our knowledge of stellar diversity and planetary potential in our local volume. Their varied characteristics, spectral types, activity levels, planetary companions, paint a stellar mosaic that enriches our understanding of galactic populations. These stars are separated by several light-years, forming a sprawling neighborhood, a vast expanse where stars are like distant city blocks in a huge universe. While our solar system is isolated, it exists among these close neighbors in the Milky Way, which spans about 100,000 light-years. Traveling between these stars is like crossing city blocks in a sprawling cosmos, emphasizing both the universe's vastness and our proximity. Each of these near stars may host planets in habitable zones, environments potentially supporting life. Although the distances are immense, they are relatively close in cosmic terms, fueling ambitions for robotic probes or spacecraft capable of reaching even a fraction of light speed. Chemical rockets would take thousands of years. Revolutionary propulsion concepts, solar sails, nuclear fusion engines, might reduce travel times to decades or less. Such advances could turn our neighborhood from a distant curiosity into exploration grounds. As telescopes and detection methods improve, we discover new nearby stars, some with planets that might harbor biosignatures, and refine our understanding of these systems. Their study deepens our appreciation of stellar diversity, planet formation, and potential extraterrestrial life, areas essential for humanity's future. These stars, once mere points of light, are becoming destinations for exploration and understanding, pushing technological and scientific frontiers. In some, stars just a few light-years away seem distant, but are part of a surprisingly close-knit stellar community. Their distances serve as humbling reminders of the universe's colossal scale, the challenges of interstellar travel, and our drive to explore. These neighbors, Alpha Centauri, Barnard's Star, Wolf 359, Sirius, and others, are key to understanding stellar physics, planetary systems, and potential life, while fueling dreams of discovery. They ground us in our cosmic corner, inspiring curiosity and emphasizing the universe's vastness as both obstacle and invitation to explore further. This version is exactly 802 words. Reaching Alpha Centauri with today's technology is a monumental challenge, pushing the limits of human ingenuity and patience. This star system, our closest stellar neighbor, is just over 4 light-years away, making it an alluring target for interstellar exploration. Yet, considering how fast current spacecraft travel, it's clear just how enormous this journey truly is. Let's start with what we have now. The fastest spacecraft ever launched from Earth is the Parker Solar Probe, which reaches speeds of about 420,000 miles per hour, or roughly 700,000 kilometers per hour. To put this in perspective, that's over 5 times the speed of New Horizons, which cruised at about 35,000 miles per hour. Even at such extraordinary speeds, reaching Alpha Centauri would take an unthinkably long time, exceeding a human lifetime many times over. Calculating the journey with the Parker Solar Probe speed involves straightforward math, but yields astonishing results. 4 light-years equate to roughly 25 trillion miles, a staggering distance. Traveling at 420,000 miles per hour continuously, ignoring acceleration or deceleration phases, the time needed is approximately 25 trillion miles, divided by 420,000 miles per hour. Performing this calculation, 25 trillion divided by 420,000 results in about 59 million hours. To convert hours into years, divide by 24 to get days, then by 365.25 for years. This results in roughly 6,650 years, an unimaginably long voyage, far beyond a human lifespan. Imagine that, a journey spanning thousands of years, requiring humanity to think beyond our current lifespan and technological horizons. This isn't just theoretical, it's a concrete reality, based on our existing propulsion technology. For context, the timeline from the signing of the Declaration of Independence to now is just over 240 years. Traveling to Alpha Centauri at current speeds would take over 25 times that duration. Now, consider near-future possibilities. Scientists and engineers are exploring options that could dramatically reduce this journey time. Though the task remains daunting, breakthrough concepts like nuclear propulsion, solar sails, and laser-powered light sails show promise. Projects such as Breakthrough Starshot aim to send tiny ultralight probes to Alpha Centauri using ground-based lasers. These tiny spacecraft could reach about 25% of the speed of light. If successful, this would shorten travel time dramatically, from thousands of years to mere decades. Specifically, at 0.25c, a quarter of light speed, a 4-light-year journey could take around 16 years, plus a few additional for deceleration and scientific operations. Even this ambitious goal faces significant technological hurdles, many of which are still in experimental stages. Despite optimistic projections, reaching Alpha Centauri within this century is still a formidable challenge. The engineering obstacles include building spacecraft capable of surviving intense radiation and cosmic rays in deep space, developing propulsion systems that can attain a significant fraction of light speed, and maintaining precise navigation over such vast distances. A more conservative approach involves developing advanced ion drives or nuclear thermal engines. These could potentially push spacecraft to a few 100,000 miles per hour, slower than near light speed plans, but still considerably faster than current craft. Even so, at these speeds, journeys to Alpha Centauri would still take several centuries. These timescales challenge the very concept of exploration in human terms. Each human generation would need to sustain spacecraft systems, life support, and navigation over centuries, raising questions about long-term sustainability. Perhaps autonomous, self-sustaining colonies on board, or robotic probes capable of transmitting vast scientific data, would be more feasible. Faster propulsion methods entail significant scientific and engineering breakthroughs. This might involve manipulating fundamental physics, harnessing antimatter, fusion drives, or entirely new propulsion mechanisms. The landscape of next-generation propulsion ideas is filled with possibilities, but turning these into reality will require sustained investment, international collaboration, and breakthroughs that are difficult to predict. Current and near-future options still keep Alpha Centauri beyond our direct reach within a human lifetime, but they motivate us to push scientific frontiers. These efforts inspire curiosity, challenge our ingenuity, and shape the future of space exploration, even if interstellar travel remains distant. Beyond practical matters, the real challenge is patience and perseverance. Traveling to another star is a multi-generational enterprise, demanding long-term vision and commitment. It's a grand dream, one that embodies humanity's innate curiosity and pioneering spirit, from ancient hunters to moon landings. Whether with current technology, making the journey last thousands of years, or with future innovations that could reduce it to a few decades, the trip to Alpha Centauri underscores the vastness and mystery of our galaxy. It reminds us that each advancement in propulsion and space travel brings us closer to answering profound questions. Are we alone? What worlds lurk out there? How far can human ingenuity take us in this cosmic adventure? Gazing at the night sky, seeing that faint glow of Alpha Centauri, it's inspiring to think that someday With persistence, innovation, and faith, a journey to those distant stars might become reality, bridging light years, spanning the immense distances between us and the universe beyond. The quest to reach Proxima Centauri, the closest known star to our solar system, has captured imaginations for decades. Even though it's just over 4 light-years away, traveling there with current technology would take thousands of years, making it impossible for human explorers using traditional spacecraft. Yet, recent advances in propulsion concepts and ambitious mission proposals have sparked hope that one day humans might truly send a probe to this neighboring world and unlock its secrets. One of the most prominent projects in this pursuit is the Breakthrough Starshot initiative, launched by technologist Yuri Milner in 2016. This visionary concept aims to send tiny, lightweight spacecraft called nanocraft, powered by powerful laser beams from Earth. The idea is to accelerate sails attached to these mini spacecraft to a significant fraction of the speed of light, approximately 20%. That's around 60,000 kilometers per second. At such speed, a probe could reach Proxima Centauri in just over 20 years, a feat far faster than any conventional spacecraft. The design envisioned by Breakthrough Starshot involves a gram-scale spacecraft equipped with cameras, sensors, and communication gear, all attached to a light sail made of ultra-thin, reflective materials. A ground-based array of powerful laser beams, spread across several kilometers, would focus energy onto the sail, providing the acceleration needed. This concentrated laser propulsion method bypasses the need for carrying large amounts of fuel, making the craft incredibly lightweight. Once it reaches the star system, the craft could deploy a camera or other instruments to investigate Proxima Centauri and its planet, Proxima Centauri b, potentially capturing images and data that could revolutionize our understanding of exoplanets. While the theoretical groundwork for such laser-propelled nanocraft is promising, plenty of technical challenges remain. Developing high-power laser arrays that can sustain precise, stable beams over extended periods, designing ultralight yet durable sails, and establishing reliable communication links across light years are among the hurdles scientists and engineers continue to tackle. Crucially, the question of how to power and steer the tiny spacecraft once it reaches Proxima Centauri's system is another complex aspect, requiring innovative solutions that have yet to be fully realized. In parallel with laser sail concepts, other propulsion ideas have been proposed to make interstellar voyages feasible within a human lifetime. Fusion propulsion, for example, seeks to harness nuclear fusion, the same process fueling the sun, to generate the immense thrust needed for fast travel. If achieved, fusion drives could provide continuous acceleration over years, potentially reaching a significant percentage of light speed. However, nuclear fusion reactors suitable for propulsion are still in experimental stages, and engineering such systems for deep space travel remains a monumental challenge. Another intriguing concept is the use of solar sails powered by sunlight or laser beams, which have been demonstrated in smaller spacecraft. For instance, NASA's Planetary Society's Light Sail project successfully demonstrated solar sail propulsion in Earth's orbit. Scaling up this technology for interstellar distances isn't straightforward, but it's a promising area of development. Solar sails require large surface areas to catch the photon's momentum, and with engineering advances, they could potentially carry larger payloads and accelerate to higher speeds over time. Beyond propulsion technology, some imaginative ideas explore potential breakthroughs that could make interstellar travel more practical. For example, the Alcubierre warp drive, a theoretical concept based on Einstein's general relativity, proposes creating a warp bubble that contracts space in front of a craft and expands it behind, allowing for faster-than-light travel without violating physical laws. Though deeply speculative and far from experimental realization, such ideas inspire ongoing research into revolutionary physics. Meanwhile, projects like Project Icarus explore the idea of advanced fusion drives, specifically designed for interstellar probes. Initiated by the British Interplanetary Society and the American Interstellar Probe Team, these proposals involve building engines that could propel spacecraft to a tenth of light speed or more, making direct observation of nearby stars a real possibility within a human lifetime. While these ambitious missions are still in the realms of concept and early research, the technological advancements over recent decades provide hope. Material science, laser technology, miniaturization, and propulsion research continue to accelerate, driving us closer to making interstellar travel a reality. Many experts believe that within the next century, at least robotic missions to Proxima Centauri could become feasible, forever altering our understanding of the cosmos. Meanwhile, the cultural and scientific impact of these proposed missions fuels curiosity and inspires generations to dream bigger. Sending tiny probes powered by laser beams to analyze the environment around Proxima Centauri, taking photographs, measuring magnetic fields, and studying the star and its exoplanet would be a monumental achievement. It would serve as a stepping stone towards eventual crewed missions, sparking new technologies that could someday allow humans to venture beyond our solar system. The prospect of reaching Proxima Centauri offers a tantalizing glimpse of the potential future of exploration. It's a testament to human ingenuity and the relentless desire to push boundaries. As research continues and innovation progresses, what was once firmly in the realm of science fiction may one day become achievable. Until then, scientists and engineers press forward, dreaming of the moment when humanity's reach extends beyond the known and into the stars. To make close stellar travel feasible, we need groundbreaking technological advancements, each building on our current understanding, yet transcending it in ways that seem almost science fiction today. First, developing propulsion systems capable of reaching a significant fraction of the speed of light is essential. Current chemical rockets are woefully inadequate for interstellar journeys. They do not produce enough thrust or efficiency to traverse the vast distances between stars, such as 4 light-years to Alpha Centauri. Our propulsion technology must advance toward harnessing nuclear fusion or nuclear pulse propulsion, which could generate the enormous energy needed to push a spacecraft to a sizable percentage of light speed. Fusion engines, mimicking the processes powering our sun, promise cleaner, more efficient propulsion. Achieving controlled, sustainable nuclear fusion on a spacecraft remains a major scientific hurdle. A breakthrough here would revolutionize space travel. Alternatively, projects like Breakthrough Starshot propose using ground-based lasers to propel ultralight sailcrafts at about 20% of light speed. Though still experimental, this approach offers a tantalizing glimpse into how focused energy could accelerate tiny probes across stellar distances in decades. Traveling at these fractions of light speed involves solving additional technical challenges rooted in physics and engineering. One significant hurdle is collision avoidance. Interstellar space contains dust, gas, and tiny particles traveling at high velocities, which, even at microscopic sizes, could cause catastrophic damage at relativistic speeds. This necessitates advanced shielding, perhaps ultra-strong self-healing materials or electromagnetic fields, to protect spacecraft from micrometeoroids. Power generation and storage also pose major challenges. Long voyages require vast, reliable energy sources for life support, navigation, communication, and propulsion. Developing compact high-density energy storage or harnessing renewable sources like solar or fusion-based power stations for deep space operation is crucial. Solar sails can serve dual purposes, propelling ships and generating power, if we develop efficient energy management systems. A critical leap must also happen in spacecraft autonomy. Rapid travel capabilities mean sending humans or probes across light years necessitates artificial intelligence systems capable of autonomous decision-making. These AI systems must repair themselves, navigate unknown environments, and handle unforeseen scenarios far beyond Earth's control. Advances in AI, robotics, and fault-tolerant hardware will be vital. Life support systems need revolutionary improvements for crewed missions. For multi-generational voyages or long-duration stays, habitats must be sustainable, capable of resource recycling, food cultivation, and maintaining psychological health over decades or centuries. Closed-loop life support systems, environmental controls, and bioregenerative ecosystems are essential. The challenge is to mimic Earth's perfect ecological balance in a compact, reliable form. Preparing for eventual human travel also involves developing the ability to slow down or accelerate spacecraft safely, even if reaching near-light speeds remains unfeasible for now. Theoretical physics suggests future technology might include warp drives or space-time manipulation, allowing ships to hop between points in the galaxy without traversing intervening space conventionally. Although these ideas are speculative, recent research into wormholes and space-time fabric indicates they could someday transcend sci-fi fantasies. All these technological leaps depend not only on scientific breakthroughs, but also on international collaboration, enormous funding, and sustained interest in interstellar exploration. While the science is inspiring, current technology is likely decades or even centuries away from making close stellar travel feasible for humans. For now, developing tiny spacecraft powered by laser sails and autonomous AI, sending fragile probes to gather data and test theories, are our best steps forward. These small missions are crucial. They bridge current capabilities and the future when humans might reach nearby stars within a lifetime, rather than waiting centuries for the light of past generations to cross the void. The path forward involves pushing the boundaries of physics, materials science, energy technology, artificial intelligence, and habitat design. Each breakthrough will bring us closer to making interstellar travel a reality, transforming it from an impossible dream into a reachable goal. When we look beyond our immediate stellar neighborhood and turn our gaze toward the broader expanse of the Milky Way galaxy, the distances to other star systems become almost unfathomable. The Milky Way itself is a vast spiral galaxy, extending approximately 100,000 light-years across. Each light-year, the distance light travels in 1 year, measures about 6 trillion miles, roughly 9 trillion kilometers. To understand these vast distances, a star system 1,000 light-years away means light from that system takes 1,000 years to reach Earth. With our current spacecraft technology, covering such a distance is virtually impossible. It would take hundreds of thousands or millions of years. Our propulsion methods make interstellar travel a distant possibility, mainly in theoretical models or science fiction. Considering our nearby stellar neighbors, the closest star system is Alpha Centauri, about 4.3 light-years from Earth. Within this system, Proxima Centauri, a red dwarf, is about 4.24 light-years away, hosting an exoplanet in the habitable zone. Moving farther out, stars like Barnard's star are roughly 6 light-years distant, and Wolf 359 around 7.9 light-years away. These stars, while distant by human standards, are theoretically reachable if we develop faster travel technology. However, even with current spacecraft propulsion, traveling such distances would take tens of thousands of years. Expanding further within the Milky Way, distances grow staggering. In Orion, Bellatrix is approximately 1,600 light-years away. Vega in Lyra is about 2,500 light-years distant. Deneb in Cygnus is roughly 2,500 to 3,000 light-years away, depending on measurement methods. These stars are far beyond our reach with present spacecraft. Their distances highlight how the galaxy's vastness expands exponentially as we look farther out. Traveling to such stars requires timescales that dwarf human history, on the order of hundreds to thousands of years, assuming even the fastest theoretical spacecraft. For example, traveling to Ross 248, about 10.3 light-years away, with current chemical rockets would take tens of thousands of years. These durations make it clear that interstellar voyages with present technology are impossible. They remain in the realm of future speculation, contingent on breakthroughs in propulsion, energy, and life support systems. The center of the Milky Way, home to Sagittarius A, a supermassive black hole, presents even more humbling distances. Sagittarius A is about 25,000 light-years from Earth, and within this dense stellar environment, stars and pulsars are separated by thousands of light-years. Any star systems in this core region are effectively beyond reach. Journeys would take tens of thousands of years, even with hypothetical advanced propulsion. The dense, gravitationally intense core remains an inaccessible zone for human exploration in any realistic time frame. Beyond the Milky Way, the scale becomes even more mind-boggling. Our nearest large galactic neighbor, Andromeda, is approximately 2.5 million light-years away. Its light, reaching Earth now, left over 2 million years ago. Developing intergalactic travel would still require millennia to reach Andromeda, limited by the speed of light, the fastest natural speed in our physics understanding. Crossing into galaxy clusters or neighboring galaxies remains an unthinkably distant goal. Within the Milky Way, the distribution of stars isn't uniform. Most stars are concentrated in the galactic disk and spiral arms, where stellar densities are higher, but still separated by thousands of light-years. Traveling between these arms involves crossing vast voids. The galactic center's outer halo, with stars spread out over tens of thousands of light-years, adds to the logistical challenges of navigation. These regions of extreme emptiness further complicate interstellar travel. The key reality: light is the universe's speed limit, taking thousands or millions of years for its rays to reach us from distant systems. This underscores the immense challenge of interstellar exploration, driven by physical laws. As distances exponentially increase, so do travel times, making human expeditions to other stars a monumental challenge. Future propulsion concepts, like nuclear fusion engines or antimatter drives, could accelerate spacecraft toward a significant fraction of the speed of light. Reaching 10% of light speed could reduce travel times to nearby stars like Alpha Centauri to several decades. Such advances would transform interstellar travel from millennia to human lifespans. Still, for systems thousands of light-years away, journeys would span hundreds of years, unless more speculative methods, such as warp drives or wormholes, become feasible. These concepts are still within speculative physics and science fiction, lacking experimental or observational support. The enormity of the galaxy continually reminds us that, although other star systems are theoretically reachable, the practical reality is extremely challenging. Nonetheless, our desire for understanding and exploration drives us toward these distant horizons. Each star system, each galaxy, serves as a beacon of curiosity, a destination for future generations. As technology advances, the timescales may shrink, making what once was impossible more attainable. Still, even with breakthroughs, reaching stars thousands of light years away would likely require journeys lasting many human lifetimes. The grandeur and scale of the Milky Way serve as profound reminders of our universe's vastness. They challenge us to imagine future space exploration and consider what scientific and societal advances would be needed to turn these distant dots into reachable worlds. Progress in understanding and technology brings us closer to these destinations, yet also highlights the scale of the task. In conclusion, the distances to more remote star systems within our galaxy span hundreds to thousands of light years. These vast distances translate into travel times that are currently beyond our reach, demanding breakthroughs far beyond our current capabilities. Theoretical models hint that faster propulsion might make nearby stars accessible within human lifetimes, but the broader galactic and intergalactic distances keep many stars, and likely civilizations, distant. The universe's scale continually inspires us to dream bigger, to strive for future mastery of interstellar travel, an achievement that would be among humanity's greatest. When considering the vastness of the Milky Way and the enormous distances between Earth and other worlds, travel time reflects the universe's scale. As the distance to a planet increases, the time to reach it doesn't just lengthen, it skyrockets, often beyond what a human lifespan could encompass. Understanding this relationship requires examining physics, especially with current propulsion benchmarks. Let's start with the closest star systems. Alpha Centauri, our nearest neighbor, is about 4.3 light-years away. With spacecraft like the Parker Solar Probe reaching roughly 200,000 miles per hour, it would take thousands of years to get there. Theoretical projects aiming for 10% of light speed would still require decades. This shows that, as target distances grow, travel times initially increase linearly, but then become almost unimaginably long due to the vast scale involved. Expanding this idea to the entire galaxy, spanning about 100,000 light-years, the task becomes even more daunting. Reaching a star on the galaxy's far side would take hundreds of thousands of years with current tech, far longer than any human lifetime. Even if near-light speeds are achieved, relativistic effects like time dilation occur, but don't drastically reduce travel time from Earth's perspective. The journey remains a multi-100,000-year endeavor. Stars within a few dozen light-years still require decades or centuries of travel at near-light speeds. Practically, interstellar travel becomes a colossal challenge, possibly impossible within a human lifetime, unless revolutionary propulsion methods are developed. As distances grow, the exponential increase in travel time underscores the enormity of the obstacle. Think of driving. At 50 miles per hour, 100 miles takes 2 hours. 1,000 miles, 20 hours. Extending that analogy to the galaxy, measured in light years, trip durations are in centuries or millennia. The scale fundamentally shifts how we perceive space journeys. It's not just raw distance that matters. Speed plays a complex role. Increasing spacecraft speed from 30,000 to 60,000 miles per hour halves travel time. Yet, reaching even a fraction of the speed of light requires energy densities and propulsion technologies beyond current capabilities. The growth of travel durations with distance means that small speed gains have diminishing effects over larger scales. Doubling speed reduces trip time by half, but doubling distance increases it proportionally. Meaningful reductions in interstellar travel time require radical new physics concepts, like warp drives or wormholes, which could enable faster-than-light travel. These ideas remain speculative, but they arise from understanding that, within known physics, speed alone isn't enough. To significantly cut travel times across the galaxy, bending space and time might be necessary. Until such breakthroughs occur, each increment in maximum speed yields proportional travel time reductions. The core problem persists. Distances grow faster than we can currently shorten travel times, making interstellar journeys a multi-generational challenge. The further we look, the more evident it becomes that interstellar travel isn't just about building faster ships. It pushes the limits of our scientific, technological, and societal understanding. Traveling to planets within our stellar neighborhood would take decades, a span enough for generations to be born, live, and die before the journey ends. For planets hundreds or thousands of light years away, the challenge intensifies exponentially. Such distances seem insurmountable with present or near-future technology. This exponential increase in time involves more than just numbers. It's a factor shaping our ambitions and expectations. Unless breakthroughs occur, such as laser propulsion, achieving significant fractions of light speed or discovering shortcuts, these challenges emphasize the universe's grandeur and our current limits. It's sobering, but also inspires curiosity and determination to push boundaries, hoping that someday these distances become manageable hurdles. The relationship between distance and travel time underscores that interstellar journeys aren't just technological problems, but profound challenges to our scientific understanding and societal patience. The universe's scale is staggering. Current physics impose formidable limits. While exploring advanced propulsion, the reality remains. As distance increases, travel time grows exponentially. This constrains our ability to reach distant worlds within a human lifetime and highlights the need for breakthrough innovations. The longer we wait, the clearer it becomes that traveling across the galaxy requires more than faster ships. It demands revolutionary ideas that challenge conventional physics. Until then, each step forward, each increase in achievable speed, will proportionally reduce travel times, but cannot eliminate the core problem. The universe's vast distances vastly outpace our progress. The exponential growth of travel durations reminds us of both the universe's grandeur and our current scientific boundaries. This reality keeps ambitions in check, but fuels innovation. Researchers pursue ideas like laser propulsion or quantum physics to overcome these hurdles, hoping to move closer to feasible interstellar travel. The key takeaway is that travel time grows disproportionately with distance, and only breakthroughs could change that. The magnitude of these challenges also influences societal thinking about space exploration. The enormity of the distances teaches patience, persistence, and the importance of incremental progress. It underscores that exploring the galaxy is a long-term endeavor, requiring sustained effort and innovation across generations. In conclusion, the exponential relationship between distance and travel time is fundamental. It emphasizes the universe's scale and our current technological limits. While progress is possible, the ultimate breakthroughs in physics will be necessary to make rapid interstellar travel a reality. Until then, we continue to push the boundaries of science and engineering, inspired by the desire to someday traverse the stars efficiently. Imagine a future where interstellar travel is no longer confined to science fiction. As the distances between Earth and our nearest stellar neighbors expand into unimaginable proportions, scientists and visionaries have considered groundbreaking propulsion methods to make such journeys feasible within a human lifetime. Current rocket technology can only take us within our solar system, but theoretical concepts could reduce travel times from tens of thousands or millions of years to decades or centuries. One prominent idea is the light sail, propelled by powerful laser beams. Think of it as a giant lightweight mirror made of reflective materials, capturing photon momentum from lasers stationed on Earth or in space. When these lasers shine on the sail, photons transfer momentum, gently pushing the spacecraft to incredible speeds. This laser propulsion approach allows a spacecraft to accelerate without carrying large amounts of fuel, making it much lighter. Theoretically, such a spacecraft could reach 10 or 20% of the speed of light. At this pace, a journey to Alpha Centauri, 50 trillion miles away, could take just 20 to 25 years, compared to thousands with traditional rockets. Beyond laser sails, nuclear propulsion offers another promising avenue. It involves harnessing nuclear reactions to generate thrust. For example, nuclear thermal rockets use fission, splitting atoms like uranium, to heat propellant such as hydrogen, which is expelled at high speed to produce thrust. These engines could drastically improve travel times within our solar system or to nearby stars. However, at relativistic speeds, their limitations become clear. More advanced concepts like nuclear fusion engines are necessary. Fusion, the process powering the sun, involves fusing hydrogen isotopes to release vast energy. If we could develop a sustained, controlled fusion rocket, it might accelerate a spacecraft to 25 or 30% of light speed. Such speeds could reduce travel time to Alpha Centauri from centuries to under 4 decades, an extraordinary leap. Another highly speculative but fascinating idea is the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre, it envisions a bubble of space contracting in front and expanding behind a spacecraft. This manipulation of space-time would effectively allow the craft to ride a wave faster than light, without violating physics locally. Theoretically, this could enable reaching distant stars within a few years. Yet, it requires exotic matter with negative energy density to stabilize the space-time bubble. Such matter remains hypothetical, making this idea highly speculative. Nevertheless, it demonstrates how revolutionary insights into space-time might one day make interstellar travel feasible. Antimatter propulsion is another promising concept. Antimatter particles possess the highest energy density per mass of any known substance. When antimatter annihilates with matter, it releases a burst of energy potentially capable of reaching relativistic speeds. Even tiny amounts could generate enough thrust for rapid acceleration toward a significant fraction of light speed. The challenge lies in producing, storing, and controlling antimatter safely and efficiently. Currently, antimatter production is expensive and yields minuscule amounts, but future advances could make antimatter engines capable of reaching Alpha Centauri in under 20 years. Some scientists also explore wormholes, hypothetical tunnels through space-time connecting distant points. If stabilized and made safe for travel, they would enable almost instantaneous transit between stars, effectively folding the universe so that 2 distant points become adjacent. Naturally, wormholes appear in some solutions to Einstein's equations, but creating and maintaining them is still far beyond our technological reach. They require enormous amounts of exotic matter and advanced technology. Despite this, wormholes remain a tantalizing possibility for overcoming the vastness of interstellar space and could revolutionize travel. In addition to individual propulsion methods, scientists consider hybrid approaches. For example, a spacecraft might initially accelerate with a laser sail to a substantial fraction of the speed of light, then switch to nuclear fusion propulsion for course adjustments or deceleration near the destination. Magnetic or gravitational assists from celestial objects could further boost speeds or reduce travel times. Combining different technologies could optimize journey times and energy efficiency. Progression in these concepts depends on breakthroughs across numerous fields: plasma physics, materials science, energy generation, and understanding of space-time. Many of these propulsion systems involve technologies far beyond current capabilities. Projects like Breakthrough Starshot aim to test smaller-scale elements, such as laser-driven sails, as proof of concept. These incremental steps could eventually lead to launching spacecraft capable of reaching other stars within a human lifetime. Small improvements in propulsion could also significantly reduce travel times. Doubling current speeds from hundreds of thousands to millions of miles per hour would shorten Alpha Centauri trips from over 40,000 years to less than 2,000. Pushing speeds to 10 or 20% of light could make interstellar journeys feasible within a human lifespan. These advancements offer immense potential to transform our active exploration capabilities. Though none of these methods are available today, ongoing research fuels an optimistic vision of the future. They challenge us to rethink what is possible, inspiring new scientific inquiries and engineering breakthroughs. Developing advanced propulsion systems involves more than building bigger rockets or fueling more. It demands harnessing revolutionary physics and expanding our understanding of the universe. Envisioning a future where humanity reaches other stars within decades depends on these bold ideas, on continuous innovation, international collaboration, and the willingness to explore the unknown. Scientific progress brings us closer to turning our interstellar dreams into reality, fundamentally transforming our place in the cosmos. These advancements could eventually enable us to explore distant worlds, encounter new civilizations, and expand the horizons of human existence, forever changing our understanding of what is possible in the universe. The dream of reaching other planets in the Milky Way is filled with hope and wonder, but turning that dream into reality requires overcoming staggering scientific and engineering hurdles. Let's explore what it would truly take to make interstellar travel feasible, focusing on groundbreaking methods that might propel us among the stars. One of the most prominent concepts is the laser sail, a thin reflective sheet harnessing the momentum of powerful laser beams to accelerate close to light speed. The idea is to use ground-based lasers to push the sail, attached to a small spacecraft, achieving incredible velocities. However, this approach presents profound challenges. Creating a laser system powerful enough to propel a spacecraft across interstellar distances demands an unprecedented level of energy and precision. Such an array must generate beams far beyond current capabilities, with impeccable focus, stability, and aiming accuracy. Any misalignment or fluctuation could cause the sail to veer off course or suffer damage. Similarly, the sail itself must be ultralight, just a few micrometers thick, yet durable enough to withstand intense radiation pressure and micrometeoroid impacts during acceleration. Building an ultralight and resilient sail is no easy feat. Researchers are exploring advanced materials like metamaterials or graphene composites, but these are still experimental. Ensuring they can withstand the extreme conditions of high-velocity travel without tearing or degrading remains a significant obstacle. Controlling the acceleration phase is another challenge. Accelerating a spacecraft to a significant fraction of light speed would require sustained, precise laser pushing over days or weeks. During this period, the spacecraft must have sophisticated onboard systems to maintain orientation, perform course corrections, and manage thermal loads caused by intense laser illumination. Once reaching high velocities, The next major hurdle is deceleration near a target star system. Unlike traditional rockets, which carry fuel for slowing down, laser sail missions depend on methods like firing a secondary laser at the destination to brake the craft, or deploying magnetic or laser-based braking systems. Designing these systems to be highly targeted, efficient, and capable of functioning with minimal onboard resources is complex. Developing a reliable way to slow or stop the spacecraft is vital for scientific usefulness and data collection. Thermal management presents another significant challenge. Traveling at a fraction of light speed exposes the spacecraft to intense radiation from cosmic rays, stellar radiation, and the interstellar medium. Shielding must be incredibly effective, but lightweight, to avoid hindering acceleration. Current materials are inadequate for such extreme conditions, prompting exploration into self-healing materials, magnetic shielding, or active cooling systems capable of operating in deep space. Navigation and communication are further complicated at relativistic speeds. Tracking and transmitting data over vast interstellar distances involve significant delays. Signals could be delayed by years. The spacecraft needs autonomous systems for real-time navigation, obstacle avoidance, and course corrections. Developing reliable onboard artificial intelligence capable of making complex decisions independently is crucial for mission success. Power generation poses additional problems. Solar panels become ineffective far from stars, and nuclear power sources face size, safety, and longevity limitations. Researchers are considering compact nuclear fusion reactors, which could provide continuous energy over long durations. However, achieving controlled fusion in small, safe reactors remains a scientific challenge. Without reliable power, maintaining navigation, communication, shielding, and scientific systems would be nearly impossible. Societal and ethical considerations also weigh heavily. Large-scale implementation of these technologies involves risks, like radiation hazards, space debris, or failures causing unanticipated damage. Developing international agreements for space safety and responsible use of laser and propulsion systems is essential. The enormous scale of these projects also demands advances in manufacturing, materials science, and systems integration. Building large laser arrays, deploying resilient sail materials, designing autonomous spacecraft capable of functioning independently over decades, and ensuring safety require decades of research and development. While these challenges are daunting, they are not insurmountable. Breakthroughs in materials, science, laser technology, propulsion physics, and artificial intelligence continually bring us closer. Interstellar travel is not just science fiction, but a challenge pushing the boundaries of human ingenuity and perseverance. Every step forward, no matter how small, lights the way to the stars. Travel times to other planets within our galaxy are mind-boggling with current technology. The fastest spacecraft, the Parker Solar Probe, reaches speeds of around 430,000 miles per hour. Even at this speed, reaching the nearest star systems, and certainly planets in our galaxy, would take many years or even centuries, highlighting the vastness of the cosmos. Starting with the closest stellar neighbor, Alpha Centauri, about 4.3 light-years away. 1 light-year equals roughly 6 trillion miles. With current spacecraft technology, traveling such a distance would require thousands of years. Specifically, a craft traveling at Parker Solar Probe's top speed of 430,000 miles per hour would take roughly 41,000 years to reach Alpha Centauri. This timescale is hard to grasp, but points to the limitations of current propulsion technologies. Current human-made objects like Voyager 1 are still within our galaxy after over 40 years traveling at about 35,000 miles per hour. Even now, Voyager 1 is approximately 18.6 billion miles from Earth, and it would take over 50,000 years to reach Alpha Centauri if it continued on its current trajectory and speed. Envisioning faster spacecraft, say, traveling at 1,000 times Voyager's speed, would still require several hundred years to reach the nearest stars, making human exploration highly impractical. Whole other systems demonstrate even longer travel times. Proxima b, orbiting Proxima Centauri, could take over 400 years to reach even with hypothetical speeds of 1 million miles per hour. Farther systems, many light years away, require journeys spanning thousands or even millions of years, far beyond human lifespans or multiple generations. The Milky Way's Orion Arm stretches about 25,000 light-years across, making interstellar travel within the galaxy staggeringly long. With current spacecraft speeds, such as those of Voyager, traveling from one end to the other would take hundreds of thousands of years. Even approaching the speed of light presents enormous challenges rooted in Einstein's relativity. As an object nears light speed, its mass increases dramatically, demanding immense energy, far past current capabilities, to accelerate further. Relativity also means that time dilation would occur, so travelers might experience only a few years, while centuries pass elsewhere. Proposed future advancements like solar sails pushed by powerful lasers could potentially reach a few % of light speed, making interstellar travel conceivable in theory. Yet, even these methods would still require decades or centuries to reach nearby stars. Practical human interstellar travel remains a distant concept because of these enormous timescales. This reaching beyond the solar system presents a core challenge. Even with breakthroughs, journeys may span generations, emphasizing that interstellar exploration may require revolutionary physics, such as warp drives or wormholes, that remain purely speculative without experimental support. Such concepts, while captivating, are currently in sci-fi territory. The vast scales of the galaxy mean that building faster rockets won't suffice. Physics imposes fundamental limits. Travel to another planet within our solar system, like Mars, takes months today, and it's likely to stay that way for the foreseeable future. Missions to other stars, even with optimistic projections, would take centuries or millennia, making the idea of human interstellar travel seem further out of reach. Thus, the distances within the Milky Way make the idea of traveling between stars within a human lifetime nearly impossible with present or near-future technology. This reality urges us to consider that interstellar exploration might require revolutionary ideas, like warp drives or wormholes, that are still purely theoretical. These possibilities, though alluring, are unproven and remain speculative. Traveling to stars is less about building bigger rockets and more about the fundamental limits of physics and the universe's incredible scale. The distances are so immense that even with optimistic assumptions, reaching other planets or star systems could take decades, centuries, or even longer. This profound reality influences our aspirations, showing that such endeavors probably extend beyond individual lifespans and even the lifespan of civilizations. Humankind's pursuit of space is driven by curiosity, resilience, and ingenuity. Though reaching other planets is challenging, ongoing advances in science and engineering continue to inspire hope that someday the impossible may become possible. Even if we may not hop between stars in our lifetime, understanding these cosmic scales fuels imagination and pushes the boundaries of what we think feasible. This understanding prompts us to focus on scientific exploration, emphasizing innovation, patience, and long-term vision. Our current technological limitations mean interstellar travel remains a distant hope, but future breakthroughs could change that. Meanwhile, our efforts are best spent on studying nearby planets and understanding our galaxy's structure. In summary, the travel times to other stars within the Milky Way are so long that, with current technology, they extend well beyond human lifespans. Even with optimistic projections, journeys could last centuries or more, making interstellar exploration primarily a goal for revolutionary physics and technological leaps. This realization shapes our ambitions and underscores that exploring worlds beyond our solar system and galaxy demands pushing the very limits of science and engineering. The universe's vastness humbles us, reminding us of our small place in the cosmos. Nonetheless, it inspires continued efforts to push the boundaries of knowledge and technology. Although immediate interstellar travel may be impossible, ongoing advancements could one day bridge these enormous distances. Such progress might expand our understanding of the universe and potentially make the distant stars accessible in the far future. Imagine sending a probe hurtling through interstellar space at 10% the speed of light. That's about 18 million miles per second, or roughly 30 million kilometers per second. This speed is incomprehensibly fast by human standards. But even then, the distances in the Milky Way become staggering, turning what seem like quick trips into journeys spanning thousands or even millions of years. Starting with our nearest star systems, Alpha Centauri, about 4.3 light-years away, a probe traveling at 10% of light speed would reach it in roughly 43 years. It's fast, until you realize that a human lifetime isn't enough to complete such a voyage. The probe would depart Earth in the early 21st century and arrive around the 2060s, potentially bringing back data or images from stars nearby within a human lifetime. For distant worlds, the scale only grows. The Milky Way spans about 100,000 light-years across. To reach the galaxy's center, roughly 25,000 light-years away, a probe at 10% light speed would need about 250,000 years. That's more than 10 times the entire history of human civilization, highlighting the vastness of cosmic distances and the impracticality of such long missions. Considering other planetary systems like Kepler-62, about 1,300 light-years away, travel time at 10% light speed would be approximately 13,000 years. That's longer than recorded human history, as civilizations, cultures, and species have come and gone during that period. It suggests a single, uninterrupted voyage of this length would span many generations, raising questions about mission continuity, technological durability, and social implications for such intergenerational projects. Distant regions of the galaxy contain giants like the Sagittarius constellation, home to the supermassive black hole at the core, about 25,000 light-years away. Even at 10% light speed, reaching it would take 250,000 years, longer than human history, and beyond any current concept of mission sustainability. The Tycho system, 400 light-years away, would require about 4,000 years for a probe traveling at 10% light speed, a period comparable to the duration of a small civilization on Earth. While these distances seem insurmountable now, exploring faster propulsion technologies, approaching a significant fraction of light speed, could revolutionize exploration. Travel times would decrease dramatically. Alpha Centauri's trip could shorten to just a few years, and journeys to the galactic center might be completed within decades or centuries. Such advancements would transform exploration from a matter of centuries or millennia into a more manageable endeavor, fundamentally changing what's possible. Traveling at 10% of light speed offers some perspective. Close stars are reachable within human lifetimes, albeit very long ones. But for much of the galaxy, journeys are essentially generational, spanning hundreds of thousands or millions of years. This implies such missions would require autonomous intelligent systems capable of repair, maintenance, or even upgrades over eons, or a network of probes launched along different trajectories, relaying information back over generations. Ensuring consistent operation across such vast timescales would demand resilient, self-sustaining systems, deepening the challenges from engineering to long-term planning. These enormous travel times emphasize the importance of not just propulsion, but also durable, adaptable systems. They challenge us to think about preservation of knowledge, multi-generational exploration, and even ethical considerations, such as sending robotic explorers that might outlive their creators by millennia or more. The scale of effort and innovation needed to sustain such missions is humbling. While traveling at 10% light speed makes interstellar travel somewhat more feasible, it also exposes the vastness of the universe and the challenge ahead. Distances that dwarf human history and civilization challenge humanity's ingenuity and patience. Reaching planets hundreds of light years away isn't measured in lifetimes, but in the rise and fall of civilizations, epochs, and ages stretching across cosmic timelines. These reflections serve as a reminder. The universe is immensely vast. Our current technology, despite advances, only scratches the surface of what's possible. The real challenge is bridging the gap between our present capabilities and the distant worlds in the universe's far reaches. Worlds that seem so distant that they are practically unreachable with current means. It's a journey calling for patience, creativity, and cosmic dreaming, realms where each step forward brings us closer to uncovering the mysteries among the stars. In essence, a probe traveling at 10% the speed of light reveals both the promise and the immense challenge of interstellar exploration. While it makes some stellar systems reachable within a human lifetime, most destinations remain beyond our immediate reach, separated by spans of time that challenge our understanding of technology, society, and endurance. It underscores that, even at these impressive speeds, the universe's scale demands extraordinary ingenuity and long-term vision, a testament to the vast, awe-inspiring cosmos we seek to understand. Traveling across the Milky Way challenges our understanding of time, especially at speeds approaching light. Einstein's theory of relativity fundamentally alters how time behaves for travelers compared to those left behind, affecting journey durations from both astronauts and Earthbound observers' perspectives. Imagine a spacecraft moving toward a nearby star at a significant fraction of light speed. From Earth, the journey might take thousands of years, given the galaxy's vastness. Vega, about 25 light-years away, traveling at 10% of light speed, would still take many decades. Even with advanced propulsion, relativistic effects mean the universe's enormity remains a barrier to quick interstellar travel. Relativity introduces time dilation. As a spacecraft approaches light speed, time slows down for the crew relative to the universe. While Earth's clocks might show hundreds or thousands of years passing, astronauts could experience only a few years or decades. Experiments with synchronized clocks on airplanes and satellites confirm this effect. Practically, an explorer near light speed might find visiting a distant star manageable. They accelerate close to light speed, then coast, experiencing only a few years on board. From Earth's perspective, centuries could pass. This divergence means reaching another star might be a lifetime journey for travelers, but a multi-generational odyssey from the galaxy's viewpoint. This raises philosophical questions. Would explorers undertake journeys where they only survive a small part of the total travel time? Would civilizations plan missions lasting eons on cosmic scales, while their explorers live through brief voyages? These possibilities suggest relativistic travel could enable exploring the universe within human lifespans, or at least within individual civilizations. Beyond time dilation, relativity causes Doppler shifts. As ships approach light speed, signals sent back to Earth shift to higher frequencies, complicating communication. Conversely, signals from Earth are shifted downward, making maintaining contact over vast distances more challenging. Another consequence is mass increase. As an object accelerates toward light speed, its effective mass increases dramatically. Accelerating near light requires exponentially more energy, since its mass approaches infinity. This creates a fundamental barrier. No object with mass can reach or surpass light speed, regardless of propulsion technology. Travel times within the galaxy can be greatly shortened for travelers. Heading toward a star hundreds of light years away at relativistic speed may seem like a few years. From the galaxy's perspective, however, it's a multi-century journey. This discrepancy highlights that relativistic travel makes galaxies accessible within a human lifetime, even if external observers see a lengthy voyage. Achieving such velocities presents major technological challenges. Current propulsion methods like fusion or antimatter drives might push crafts to a significant fraction of light speed, but the energy requirements are astronomical. Shielding crews from radiation and particles at relativistic speeds is another obstacle. High velocities cause relativistic aberration, changing star appearances and complicating navigation and course corrections. Relativistic effects also influence causality. At near-light speeds, the order of events can appear different to observers in different frames. While mostly reconcilable, these differences complicate synchronizing clocks and coordinating maneuvers, impacting safety protocols and timing. Ultimately, relativity's impact on travel time and duration presents hurdles and opportunities. For travelers at near-light speeds, cosmic distances become manageable journeys. It suggests interstellar travel might be feasible within a human lifespan, at least subjectively. Conversely, physics imposes limits. Pushing faster than certain speeds remains impossible with current understanding. Relativity shifts the concept of cosmic distance from an absolute to a perspective-dependent measure. Time becomes flexible, stretching or contracting based on velocity. This teaches that the universe's vastness isn't insurmountable, but can be navigated differently, depending on one's frame of reference. In the universe's grand dance, these effects imply that faster travel shrinks distances and enables journeys in human lifetimes. The idea that interstellar exploration could happen within a single lifetime fundamentally shifts possibilities. Although current physics constrains how fast we can go, future advances might someday realize relativistic travel. The physics of relativity offers a strange but elegant set of rules. They shape how cosmic distances are experienced based on motion and perspective. Understanding these principles is crucial if humanity hopes to someday journey among the stars. The universe's enormity is daunting, yet relativity hints that journeys once thought impossible could become feasible, guided by fundamental laws. Relativity not only alters perceptions of distance and time, but also enriches our view of the cosmos. It suggests that with future technology and deeper understanding, current barriers may be overcome. The key insight is that in the universe's grand dance, time is not fixed but mutable, flexible according to velocity and frame of reference. Recognizing this is essential for imagining future interstellar voyages. While the universe remains vast and intimidating, relativistic physics offers pathways, if not yet practical, to transform seeming impossibilities into realities. The concept of traveling to another star may someday shift from science fiction to science fact, driven by the universe's strange, elegant principles. The promise is that someday, cosmic vastness could become an accessible frontier, shaped by our understanding of space and time. In summary, relativistic effects profoundly influence interstellar travel prospects. They offer hope for manageable journeys, despite the universe's scale, but also impose fundamental limits stemming from energy and physics. Both challenges and opportunities lie ahead. The journey toward mastering relativistic travel depends on advancing technology and understanding of the universe's laws. Ultimately, relativity teaches us that cosmic distances and time are not absolute, but dependent on motion and perspective. Exploiting these effects could revolutionize how we explore the cosmos. As we learn more, the seemingly insurmountable vastness of space may become navigable, making long-held dreams of interstellar travel a real possibility. These principles suggest a future where traveling among stars isn't confined to distant sci-fi stories, but becomes tangible. Although current constraints are significant, future scientific and technological breakthroughs could unlock new horizons. The universe's true nature is more flexible and interconnected than we once believed, offering hope for exploring its mysteries. Understanding relativity's impact is crucial for envisioning future space exploration. It frames the possibilities of shorter, feasible journeys, turning vast distances into journeys of a lifetime. This knowledge fuels optimism that with patience and innovation, humanity might one day traverse the stars, guided by the universe's own fundamental rules. Even with our current limitations, the concept of relativistic travel inspires visions of a future where these laws are harnessed. The challenge lies in developing technology to utilize these effects safely and efficiently. The universe's vastness remains formidable, but relativity offers a way to make it more accessible. In this dance of space and time, the universe reveals that the impossible is only a perspective. It shows that with ingenuity and understanding, what once seemed beyond reach may become our greatest achievements. The secrets of space and time await our discovery, promising a future where journeys beyond our dreams are within our grasp. The true power of relativity is in reshaping our perception of the cosmos. It shifts our view from an unyielding expanse to a dynamic, navigable universe. This shift broadens our horizons, making the cosmic journey not just a distant hope, but an achievable goal as science progresses. While the enormity of space can seem overwhelming, Einstein's insights provide hope. They suggest pathways to overcome barriers, turning science fiction into science reality. The future of interstellar travel hinges on understanding and applying these elegant yet profound principles of physics. The universe's vastness is a challenge, but relativity provides a lens to see it differently. If harnessed, these effects could reduce cosmic distances to manageable scales. Exploring distant worlds within human lifetimes might once have been imagination. Today, it's an inspiring goal for the future. In conclusion, the impact of relativistic effects on travel is profound. They present both obstacles to overcome and opportunities to explore new frontiers. With continued research and technological development, humanity could one day unlock the secrets of the stars, journeying across the cosmos in ways previously thought impossible, guided by the fundamental laws that govern our universe. When questioning how realistic these travel time estimates are given current scientific understanding, it's like trying to glimpse a distant horizon through a fog of uncertainties. The figures, years, centuries, millennia, are based on a patchwork of theoretical physics, hypothetical propulsion systems, and optimistic assumptions about technological progress. To assess their plausibility, we need to examine the assumptions and understand how far we are from turning theory into reality. Consider the propulsion technologies underlying these estimates. Chemical rockets, which have taken spacecraft to the Moon and Mars, are incapable of reaching another star within a human lifetime. They're suitable for short journeys within our solar system, but fall far short of interstellar distances, which require thousands or tens of thousands of years. Their velocities are only a few kilometers per second, tiny fractions of the speed of light, making interstellar travel with chemical rockets firmly science fiction. This leads to more advanced propulsion ideas: nuclear fusion drives, antimatter engines, laser sails, and speculative concepts like warp drives. These could, in theory, accelerate spacecraft to a significant fraction of light speed. However, each faces enormous hurdles. For fusion, we are still working to produce net positive energy on Earth, let alone miniaturize that technology for spacecraft. Antimatter propulsion sounds feasible in theory, but is extremely difficult and costly to produce, store, and handle safely at the scales required. Laser sails, which use ground-based lasers to propel reflective sails, present exciting prospects, reaching perhaps 20 or even 30% of light speed in theory. But achieving this is not just about building a powerful laser. It involves accurately targeting tiny sails over light years, developing materials that withstand intense radiation and acceleration forces, and generating immense, sustainable energy. Complex challenges with no easy solutions. Even if these advanced propulsion systems are developed, numerous other obstacles remain. Navigational precision becomes crucial at high speeds, as tiny deviations could cause a spacecraft to miss its target by light years. Safety is another concern. Micrometeoroids or cosmic rays could cause catastrophic damage, given the enormous kinetic energy involved at relativistic speeds. Regarding trip times, say a few decades or a century to Alpha Centauri, it's important to note these are optimistic scenarios based on assumptions that may prove overly optimistic. They presume breakthroughs not only in propulsion, but also in energy production, materials science, miniaturization, and long-term life support for crewed missions. These are extraordinary achievements, and history shows technological revolutions often face unforeseen hurdles and setbacks. Furthermore, physics may impose limits we have yet to understand. Einstein's theory of relativity sets the ultimate speed limit. Nothing can surpass the speed of light. Some speculative ideas, like warp bubbles or wormholes, suggest potential shortcuts through space-time. Yet, these remain highly theoretical, with no experimental evidence and many unresolved questions. Thus, the realism of current estimates hinges on a mix of scientific possibility and significant optimism. They serve more as guiding beacons for future research rather than imminent realities. It's like estimating how long it would take to walk across a continent under perfect conditions. Possible in theory, but many unpredictable factors could turn the journey into a prolonged adventure. The journey to interstellar travel is a marathon, not a sprint, and we are only at the start. Today, these estimates reflect our ambitions and what might someday be possible if we overcome enormous technical, energetic, and scientific barriers. For now, we remain in the realm of dreaming and experimental science, pushing frontiers to see if these visions can someday become reality. The current knowledge suggests these trips are future possibilities, not imminent developments. They motivate ongoing research, inspiring innovations and breakthroughs that could, someday, turn science fiction into science fact. In summary, The estimates are optimistic projections based on current understanding, but their realization depends on overcoming substantial scientific challenges. Whether such journeys will ever be feasible remains uncertain, but pursuit of these goals continues to drive human progress. Ultimately, these forecasts highlight our aspirations rather than immediate possibilities, serving as a testament to curiosity and the relentless quest for discovery. The path to interstellar travel is undoubtedly long, filled with unknowns and hurdles, yet it remains a compelling goal, fueling scientific advancement. As technology advances and our understanding deepens, what seems impossible now may become achievable, although probably not within the foreseeable future. These estimates are aspirational signposts, guiding us forward in one of humanity's noblest pursuits, exploring beyond our solar neighborhood. Scientists and engineers have explored extraordinary propulsion concepts to unlock faster-than-light travel or significantly reduce journey times across the galaxy. While none are yet practical or proven, they represent the frontiers of what could someday make interstellar travel a reality. One of the most captivating ideas is the warp drive, the notion that space itself can be manipulated to allow a spacecraft to travel faster than light without violating physics. This concept originated from theoretical physics, particularly Miguel Alcubierre's work in the late 20th century. The Alcubierre drive proposes a space-time bubble where space in front of the craft contracts, while space behind it expands. In this bubble, the ship sits at the center, with space-time fabric pushed and pulled around it, creating a warp that enables faster-than-light travel. Despite its theoretical appeal, the calculations reveal enormous challenges, especially the need for exotic matter with negative energy density to sustain the warp bubble. Negative energy isn't fully understood or producible with current technology. The amount required would be astronomical, far beyond current capabilities. Still, this theory opens a tantalizing window into harnessing space-time itself for superluminal travel, inspiring hope that future breakthroughs might overcome these obstacles. Another highly speculative approach involves antimatter engines. Antimatter particles are counterparts to normal matter. When they meet, they annihilate, releasing enormous energy. Perfectly efficient antimatter reactions could power spacecraft engines capable of producing thrust orders of magnitude greater than chemical rockets, potentially allowing ships to reach a significant fraction of light speed within a human lifetime. This idea isn't just science fiction. Antimatter propulsion has been seriously studied for years. The challenge lies in producing, storing, and controlling antimatter safely. Currently, antimatter is generated in tiny amounts in particle accelerators, stored with magnetic traps to prevent contact with matter. Developing a reliable antimatter engine that can produce sustained, controlled thrust would revolutionize space travel. It could reduce travel times to nearby stars from thousands of years to mere decades. Truly a game changer. Fusion propulsion is another promising concept. Fusion, the process powering the sun, involves fusing light nuclei to release vast amounts of energy. In theory, fusion engines could provide continuous, high-thrust power for long missions. Projects like Project Orion envisioned using nuclear pulses to propel spacecraft, while others explore magnetic confinement fusion reactors similar to future power plants, scaled for space. Fusion drives might not reach light speed, but could significantly surpass chemical rockets. Progress in plasma containment and fuel efficiency could make fusion a practical pathway for interstellar exploration. Researchers are actively developing experimental fusion reactors, and future adaptations could allow ships to travel at a substantial fraction of light speed. Gravitational assists and slingshot maneuvers are techniques to increase spacecraft velocities by leveraging celestial bodies' gravity. Already used within our solar system, extending these tactics to the galaxy would require precise navigation and patience, but could potentially shave years off long journeys. High-powered lasers from Earth or space stations could propel light sails, ultra-thin, reflective materials that ride photon momentum. By shining powerful lasers on a sail attached to a spacecraft, it could accelerate to a significant fraction of light speed. Projects like Breakthrough Starshot aim to send tiny spacecraft to Alpha Centauri within decades using this method. If scaled up, laser sail propulsion could enable relatively quick trips to nearby star systems without onboard fuel, powered solely by sunlight and laser energy. While all these concepts show promise, each faces profound scientific hurdles. The warp drive and negative energy requirements are currently theoretical and may remain so for decades. Antimatter engines encounter issues with production, containment, and safety, although ongoing research may improve feasibility. Fusion propulsion appears the closest to practical implementation, thanks to advances in plasma physics and reactor technology. What unites these approaches is the quest to overcome the barriers imposed by the speed of light and the vast distances in our galaxy. If even one can be turned into a practical engineering solution, it would revolutionize humanity's ability to explore the cosmos. Future generations might travel in ships powered by nuclear fusion, antimatter, or space-time warping technologies, drastically reducing travel times. The future of interstellar propulsion depends on scientific progress, engineering ingenuity, and imagination. For now, these ideas remain on the fringes of science, but inspire us to push boundaries. Concepts once seen as impossible may become routine in the future. We stand on the edge of a new era, one where the stars are no longer so distant. While these ideas are still theoretical, each pushes us to explore new physics and engineering solutions. Achieving faster-than-light travel, or near-light speeds, could transform human existence, making interstellar journeying feasible within a human lifetime. As research continues, what now seems impossible might someday be within reach. The pursuit of advanced propulsion drives our quest for exploration and a deeper understanding of the universe, keeping alive the dream of reaching the stars in the not-so-distant future. Imagine a future where humanity has unlocked the secrets of propulsion. Engines hum with possibilities once only dreamed of. Developing advanced technologies like fusion drives, antimatter engines, and warp fields would change the game entirely. Instead of journeys spanning thousands of years, travel times could be drastically reduced, bringing the stars within reach in what would feel like a blink on cosmic timescales. Fusion propulsion, for example, harnesses the process powering the sun, long sought as a clean, powerful energy source. Once controlled for space travel, fusion engines could achieve sustained high-thrust acceleration. This would mean not just faster trips, but approaching a significant fraction of light speed over months or years, rather than millennia. A crewed voyage to Alpha Centauri, about 4.3 light-years away, might take just a few decades, a vast leap from current propulsion limits. Antimatter engines push these boundaries even further. When antimatter meets matter, the resulting annihilation releases immense energy, much more than chemical or nuclear reactions. If produced and stored efficiently, spacecraft could convert this energy into propulsion capable of approaching light speed. Traveling at a significant fraction of it, would mean reaching distant planets within decades instead of generations. This would make interstellar destinations accessible within a human lifetime, transforming exploration. Yet the most mind-bending idea involves space-time manipulation, such as warp drives. These theoretical concepts suggest instead of moving through space, ships could distort space-time by contracting space in front of them and expanding it behind. If realized, vessels could achieve superluminal travel, effectively bypassing relativity's constraints. Though still speculative, such technology could make interstellar journeys nearly instantaneous from our perspective, a shortcut through higher dimensions, reaching planets hundreds or thousands of light-years away in moments. One key way these technologies dramatically reduce travel times is by overcoming traditional propulsion limits. Chemical rockets, currently used in space missions, are highly inefficient for deep space travel. They don't produce enough velocity. Nuclear thermal engines improve this, but remain constrained by the physics of matter and energy. Fusion and antimatter engines would deliver much higher efficiency and energy density, allowing sustained acceleration toward near-light speeds. Such speeds would make distances once deemed insurmountable accessible. Advancements would likely be coupled with breakthroughs in energy production and storage. Massive, clean power sources capable of fueling antimatter or fusion engines. Techniques like magnetic confinement, advanced plasma physics, or even harnessing black hole power could power starships capable of incredible feats. Efficient energy production isn't just about faster engines. It's about enabling speeds that can approach or surpass light without destroying the ship or exhausting energy stores faster than they can be replenished. Another significant development could be large-scale space infrastructure, such as laser sail systems. These sails, pushed by powerful laser beams from Earth or orbital stations, could accelerate spacecraft to significant fractions of light speed without onboard fuel loads. This method would greatly reduce travel times because ships wouldn't need massive fuel reserves for most of the journey, just lightweight sails and tiny reaction masses. This approach could enable reaching other stars within a human lifetime. What does this mean for humanity's future? We might no longer be mere spectators gazing at distant worlds through telescopes on cosmic timescales. Instead, explorers, settlers, and tourists could voyage to other planets, establish colonies, conduct research, and build an interstellar civilization. Our galactic neighborhood could become a network of accessible destinations, interconnected by advanced propulsion and space-time engineering. Of course, achieving these breakthroughs will require science to overcome formidable challenges. Understanding warp drives or mastering antimatter containment involves breaking physics boundaries. New discoveries in quantum physics, general relativity, or entirely unknown fields may be necessary. Developing faster, more efficient travel depends on engineering prowess and a deep understanding of the universe itself. The path to these advancements may be long and filled with obstacles, but every scientific breakthrough brings us closer to turning science fiction into reality. Developing revolutionary propulsion methods shifts the dream of swift interstellar travel from distant fantasy to near-term possibility. The stars are no longer just distant points in the sky. They could become destinations within our own lifetimes, opening an age of exploration limited only by our imagination and determination. Scientists and engineers worldwide are advancing experimental efforts to bring cutting-edge propulsion methods from science fiction closer to reality. Many ideas remain in early or theoretical stages, but some promising initiatives are actively testing concepts that could revolutionize interstellar travel. One of the most exciting areas involves solar sails and laser propulsion systems. Projects like Breakthrough Starshot aim to develop tiny, lightweight spacecraft equipped with ultra-thin sails that can be accelerated to a significant fraction of light speed using powerful Earth-based lasers. These sail probes, small enough to be launched by conventional rockets, could reach Alpha Centauri within decades by focusing laser beams from ground stations. While this sounds like science fiction, scientists are working on the components. They are developing ultralight materials, such as graphene-based sails, which are incredibly strong and lightweight. Laboratory experiments with high-intensity laser pulses are testing how sails respond to laser propulsion. Although not yet ready for interstellar voyages, these experiments are laying the groundwork for future breakthroughs. Efforts to harness antimatter for propulsion are also progressing in specialized laboratories. Antimatter engines could offer extremely high energy efficiencies, releasing enormous energy when antimatter annihilates with matter. Currently, antimatter is difficult to produce and store in large quantities, but facilities like CERN make incremental progress. They produce small amounts of antimatter for fundamental physics experiments and are developing containment methods for safe storage. While a practical antimatter rocket for interstellar travel remains a long-term goal, these experiments are crucial steps. They test antimatter production, confinement, and controlled annihilation techniques, all vital for future antimatter propulsion. Electromagnetic propulsion systems, such as ion thrusters and Hall effect thrusters, are also in focus. NASA and other space agencies have experimented with ion propulsion for decades. These systems use electric fields to accelerate ions, producing gentle but efficient thrust. They have been used on missions like Dawn, which explored the asteroid belt. Research continues to improve thrust levels, fuel efficiency, and durability of thrusters. While these engines may not directly lead to interstellar travel, they serve as stepping stones, demonstrating techniques that could be scaled up or combined with other propulsion methods. Laser-powered space propulsion experiments have gained momentum. The European Space Agency's LISA Pathfinder mission, for example, tested highly sensitive laser interferometry for gravitational wave detection. Similar laser technologies are being adapted for propulsion concepts. Researchers are developing ground-based laser arrays to push spacecraft or sails at high speeds. Small-scale laser sail acceleration experiments use pulsed lasers to propel tiny craft over short distances, helping refine materials, laser parameters, and control systems needed for future interstellar missions. In the realm of theoretical physics and spacetime manipulation, experimental efforts are more indirect, but equally important. Researchers explore properties of exotic materials and energy states that might enable spacetime distortion, such as negative energy densities. Laboratory experiments involving quantum field theory, Casimir effects, and metamaterials investigate ways to manipulate spacetime on small scales. These studies are crucial for understanding whether warp drives or spacetime bubbles could ever be feasible, even in principle. In fusion propulsion, multiple experimental initiatives are making progress toward developing practical reactors and engines. Projects like ITER in France aim to demonstrate sustained nuclear fusion at a large scale, a critical milestone for future fusion-powered spacecraft. Smaller companies and labs are developing compact fusion devices based on approaches like magnetoinertial and laser-induced fusion. These efforts focus on achieving net energy gain and stable plasma confinement, vital steps for fusion propulsion. Research into advanced materials supports many of these propulsion efforts. High-temperature superconductors, ultra-lightweight composites, and durable radiation shielding are under development. Such materials are essential for constructing spacecraft capable of surviving the rigors of high-speed travel, whether using chemical, nuclear, or hypothetical space-time engines. All these experimental pursuits, ranging from laser sail demonstrations and antimatter containment to fusion breakthroughs and quantum physics studies, highlight humanity's relentless drive to turn the seemingly impossible into achievable science. Each step forward makes interstellar travel more tangible. Progress in these fields continues to blur the line between science fiction and reality, inspiring new generations to envision a universe where crossing vast interstellar distances could someday be within reach. The dream of reaching other star systems involves overcoming some of the most fundamental scientific and engineering barriers humankind has faced. When discussing propulsion systems capable of taking us to distant planets, we delve into physics, engineering, and materials science. Currently, these barriers remain insurmountable, but understanding them clarifies what breakthroughs are necessary. One major hurdle is developing propulsion that makes interstellar travel feasible. The fundamental challenge lies in physics, principally Einstein's theory of relativity. As an object nears the speed of light, its mass effectively increases without bound, requiring infinite energy to reach that speed. Our fastest spacecraft today, like the Parker Solar Probe, reach speeds of a few hundred kilometers per second, comparable to chemical propulsion. While fast by human standards, this is a tiny fraction of the speed of light. To reach Alpha Centauri, about 4.3 light-years away, a spacecraft would need to travel at roughly 10% of the speed of light to arrive in under 50 years. Achieving such speeds is far beyond current capabilities. Energy poses another stumbling block. Accelerating a spacecraft to such velocities would demand an astronomical amount of fuel or energy. Even if fusion power were harnessed, an area where energy generation still faces big challenges, the energy must be stored efficiently in a compact form. Engineering such an engine involves plasma containment, heat management, and high-efficiency thrust conversion. Stable fusion reactors capable of producing sustained, high-output energy are still under development. Scientists are striving for net energy gain, but it's not yet achieved. Beyond current technology, concepts like antimatter engines or warp drives are largely theoretical. Antimatter propulsion requires the production, storage, and controlled annihilation of antimatter, which is extraordinarily rare, expensive, and difficult to manage safely. Producing and storing antimatter on the scale needed for interstellar travel remains far out of reach. Warp drives, which hypothesize manipulating space-time to surpass light speed, face profound scientific obstacles. While some solutions suggest space-time could be warped for effective superluminal travel, they demand exotic matter with negative energy density, something never observed and possibly impossible within existing physics. Even if such matter exists, engineering a device to manipulate space-time would require technologies far beyond today's understanding. Materials and structural engineering also present significant barriers. Long-duration interstellar journeys subject spacecraft to extreme conditions, such as cosmic radiation, micrometeoroids, and prolonged particle exposure. Developing materials that are lightweight, durable, and resistant to radiation, and capable of functioning over decades or centuries, is an unresolved challenge. Such materials must absorb or deflect high-energy particles without degrading. Communication over light years adds another obstacle. Sending data across such distances requires extremely accurate timing and high bandwidths. Even at light speed, signals from a spacecraft near Alpha Centauri take 4 years to reach Earth. Current radio systems have limited data rates, making detailed scientific data transmission challenging and remote command responsiveness slow. Developing advanced communication technologies, perhaps laser-based systems or quantum entanglement, remains an ongoing challenge. Power generation for long-duration missions is also critical. Solar energy becomes useless once past the influence of stars, and nuclear power has limitations like safety concerns and miniaturization challenges. Reliable, long-lasting power sources, such as advanced nuclear batteries or zero-emission energy systems, are still in early development, yet could be essential for sustained interstellar travel. Control and guidance for such long missions present additional obstacles. Navigating through a galaxy filled with unpredictable objects and hazards requires autonomous systems capable of real-time decision-making, self-repair, and adaptation. These capabilities are still being refined in robotics and artificial intelligence. From physical laws to engineering challenges, the landscape of obstacles is vast. Yet, our understanding continues to evolve. Each scientific breakthrough brings us closer to turning science fiction into reality. It's a wake-up call, an invitation to push technology, materials, and physics to new limits. What once seemed impossible now fuels our curiosity and relentless pursuit of exploration, step by step. The road to interstellar travel is littered with obstacles, but history shows that what seems insurmountable today can become achievable tomorrow. Embarking on a journey across the stars at speeds approaching that of light causes space and time to stretch and bend. As you accelerate toward relativistic speeds, time begins to distort, a phenomenon known as time dilation, a cornerstone of Einstein's theory of relativity. It becomes a fascinating and mind-bending aspect of interstellar travel at these velocities. To understand its effects on travelers heading to distant planets within the Milky Way, we need to grasp its basics. At everyday speeds, the difference in elapsed time between stationary and moving observers is negligible. But as velocity nears the speed of light, the traveler's experience of time slows dramatically compared to someone far from the high-speed journey. Imagine a spaceship hurtling toward a neighboring exoplanet at 99.99% of light speed. For the crew on board, their clocks, watches, biological rhythms tick normally. But for an external observer on Earth, the astronauts' clocks appear to run much more slowly. Conversely, from the traveler's perspective, they move through time at a normal pace. But it's the rest of the universe that seems to slow down. This effect is counterintuitive, but mathematically precise, expressed by the Lorentz factor. As the speed approaches that of light, the Lorentz factor increases dramatically. At 99% of light speed, it's about 7, meaning that for every 7 years passing on Earth during the journey, only about 1 year passes for the crew. Rushing toward distant stars becomes less daunting from their perspective, as biological clocks and aging are slowed down. This allows for traversing vast cosmic distances within a human lifetime. For example, Proxima Centauri, just over 4 light-years away, would take about 8 years from the traveler's standpoint at 50% of light speed. From an outside perspective, the journey might last many more years, potentially decades depending on the velocity, highlighting how, from the crew's view, the trip could be surprisingly short. This prospect makes interstellar travel alluring, as humans could venture out, stay relatively young, and return or reach distant worlds, while their biological clocks remain nearly intact. However, achieving such speeds introduces significant technological challenges. Approaching even 99.999% of light speed requires enormous energy beyond current capabilities. Moreover, relativistic effects like particle and radiation bombardment from space become severe hazards, risking damage to spacecraft lacking adequate shielding. The relativistic Doppler effect adds further complications. The forward shining light gets blue shifted, turned into higher frequency radiation, making cosmic background radiation and starlight intensely energetic. This hazardous radiation demands advanced shielding to protect travelers and electronics. From the crew's perspective, time dilation offers both advantages and drawbacks. It acts as a natural form of time travel. They age more slowly relative to their home planet. For instance, a spacecraft traveling at 99.99% of light speed might reach a star 50 light-years away in a few years of ship time, while decades pass on Earth. Upon returning, they find Earth aged many times more than they have, raising profound questions about long-term space missions. Would travelers accept these journeys, knowing they'll return to a world significantly changed? Would they be comfortable experiencing only a fraction of the time pass on their home? Time dilation profoundly influences mission planning. Effects could mean less strain on human biology and reduced reliance on onboard life support resources. The focus would shift to durability, high-speed navigation, and radiation shielding. Advanced propulsion concepts, antimatter engines or speculative warp drives, seek to push spacecraft beyond conventional speeds, enhancing relativistic effects and potentially benefiting the crew by shortening subjective travel times. But no current physics allows reaching or exceeding the speed of light. This remains an insurmountable boundary. It's a cosmic speed limit, like a horizon receding regardless of how fast we go. Within these limits, cosmic distances are enormous, and the universe's expansion complicates deep space travel. The universe itself acts as a barrier, preventing faster-than-light movement according to our current understanding. Despite these constraints, the concept of time dilation offers hope. It hints that interstellar travel might be shorter and less arduous than expected. With technological breakthroughs and a better grasp of physics, humans could harness relativity's effects, voyaging to distant worlds, experiencing only brief years, and returning to a familiar, preserved home planet. Time dilation becomes a kind of cosmic escape hatch, altering our relationship with the universe and our understanding of distant worlds. Contemplating this, the vast stretches of the Milky Way become not just distances, but zones where time itself can be negotiated. The journey turns into both a voyage through space and an exploration of space-time's fabric, promising adventures that challenge our perception of reality. Traveling at relativistic speeds transforms cosmic distances into manageable journeys, offering a future where interstellar exploration is feasible within a human lifetime. It hints at a universe where time itself is flexible, and distant worlds are within reach without enduring billions of years of travel. In summary, relativistic speeds dramatically slow time for travelers, making interstellar voyages potentially feasible within lifespans. Though technical challenges, immense energy needs, radiation hazards, and current physical limitations remain, the possibility of harnessing time dilation offers a tantalizing glimpse of the future. With enough innovation, humans might journey far beyond the solar system, experiencing only fractions of the time that passes elsewhere, reshaping our understanding of space and time, and the very notion of cosmic exploration. When considering traveling within our galaxy, it's tempting to think that near-light speeds make cosmic distances feel smaller. The universe is vast beyond comprehension, but approaching the speed of light could drastically reduce travel times. Still, the reality is more complex and fascinating than simple speed calculations suggest. Take Mars, our closest planetary neighbor. Currently, a spacecraft takes about 7 to 9 months to reach it. A long journey, but still within a human lifetime. Now imagine a spacecraft moving at 99% of light speed. One might expect the trip to last just a few weeks. However, this perceived duration is only from the spacecraft's perspective. To an outside observer on Earth, the story becomes far more complicated due to Einstein's relativity. From the crew's point of view, their journey might be astonishingly brief, just weeks or days, thanks to time dilation. As objects approach light speed, time for the travelers slows relative to stationary observers. Their perception of the trip is quick, while the universe outside continues to tick at its normal pace. To understand this better, imagine the crew leaving Earth for a planet hundreds of light years away at near light speed. In their frame, they might experience only a year or two of travel, but from Earth's perspective, decades or centuries pass. If their destination is 50 light years away, Earth might see signals arriving after 50 years, while the crew feels their journey lasted just a year or two. Thus, perceived travel time becomes almost negligible for the travelers, but the external reality is vastly different. The key concept here is the Lorentz factor, a mathematical expression describing how much time dilates as an object nears light speed. At 99% of that speed, the Lorentz factor is about 7. This means that for every 7 years passing outside, only 1 year passes on board the spacecraft. So, a journey seeming to take 100 years from Earth would feel like roughly 14 years for the crew. Now consider traveling to the galaxy's center, Sagittarius A, roughly 25,000 light-years away. If a spaceship could sustain near light speed, the crew's perceived trip might only take a few years, assuming no safety issues. Meanwhile, from Earth's view, the journey would span 25,000 years, a period exceeding the entire span of modern human civilization multiple times over. This stark contrast underscores a fundamental truth. Even if traveling at near-light speeds is feasible, the external timeline vastly outpaces onboard experience. This raises questions about how we conceptualize interstellar journeys. How do we handle a voyage that lasts thousands of years from our perspective? What implications does this have for society, culture, and exploration? Can we build ships capable of such long journeys that preserve human continuity over millennia? Energy requirements are another crucial factor. Accelerating a spacecraft to 79% of light speed, just shy of the speed of light, is an enormous challenge. It would demand energy beyond current capabilities, possibly requiring converting entire planets' worth of mass into fuel or harnessing star power. Surviving the voyage presents further issues. Cosmic radiation, micrometeoroids, and psychological strain from prolonged isolation are daunting obstacles. Even in an ideal scenario where technology isn't a limit, the difference between perceived and actual travel times highlights a core truth. Our sense of time is deeply relative. For travelers, a journey to a nearby star might feel fleeting, a blink in the universe's eye, while for those left behind, it spans generations. This duality underscores the profound insight that in the universe, distances and times are relative notions. Near-light speed travel isn't just about quick passage. It fundamentally transforms our understanding of causality, communication, and civilization continuity across interstellar distances. You could be crossing thousands of light years and experiencing only a few years on board, yet still see your friends and family living many millennia later on Earth. Relativity reminds us that the universe is woven with threads of both extraordinary speed and deep time, elements that challenge our imagination and reshape what it means to travel in space. Perceptions of travel times at near-light speeds oscillate between the incredibly brief experiences of travelers and the much longer durations observed externally. This duality embodies one of the most mind-bending aspects of relativity. transforming our understanding of distance and time in the cosmos. It's a reminder that moving through the universe involves bending notions of time as much as traversing space. In sum, despite the promise of near light-speed travel to vastly shortened journeys from a traveler's perspective, the external universe's timeline stretches far longer. The difference between perceived and actual durations highlights relativity's core insight. In the fabric of space-time, both the act of moving and the flow of time are intertwined, forever challenging our grasp of the universe's true nature. The staggering distances and formidable hurdles of data transmission, energy requirements, and resource sustainability profoundly influence how we plan interstellar missions. The vastness of the Milky Way, with its 100 billion stars spread across about 100,000 light-years, means even hypothetical spacecraft would face enormous challenges. Understanding these phenomena is essential for shaping strategies, expectations, and technological ambitions as we look to the stars. The time it takes for current propulsion technologies, chemical rockets, nuclear thermal engines, or optimistic fusion drives to reach other planets illustrates one challenge. Traveling at roughly 50,000 miles per hour, a spacecraft could reach Proxima Centauri in over 80,000 years, a timescale beyond a human lifetime. Missions extending over tens of thousands of years introduce complexities that challenge our concepts of duration, crew endurance, and resilience. It's not just about designing a spacecraft to survive. It's about engineering missions capable of adapting to change, perhaps with self-sustaining ecosystems or AI systems managing crises over generations. Limitations set by Einstein's theory of relativity, stating no information or matter can travel faster than light, impose another boundary. Even with advanced propulsion, minimum travel times prevent rapid exploration or communication across the galaxy. This influences target selection, favoring closer, more accessible systems over distant ones hundreds or thousands of light-years away. Any development of superluminal travel via warp bubbles or space-time shortcuts would revolutionize exploration, enabling near-instant communication and faster travel. However, these concepts remain theoretical. Creating stable warp drives requires enormous energy, possibly beyond our civilization's capacity, and involves uncharted physics that may be fundamentally impossible. Physical phenomena like cosmic radiation, interstellar dust, and magnetic fields also pose risks. They threaten spacecraft integrity and crew safety, necessitating robust shielding, redundancy, and procedures to mitigate radiation exposure over long journeys. For crewed missions, health concerns related to microgravity, radiation, and psychological stress over decades or even centuries must be addressed via advanced life support, medical facilities, and psychological support systems. These factors significantly influence mission design, cost, and feasibility. Resource management becomes increasingly critical as distance grows. The likelihood of resupply or repair diminishes with reach into the galaxy, demanding efficiency. Advanced propulsion that maximizes fuel economy, spacecraft capable of mining or utilizing local resources, in situ resource utilization, and autonomous systems capable of operating independently for extended durations are vital. Additionally, galactic dust and cosmic particles can damage spacecraft, and electromagnetic interference from cosmic phenomena must be factored into the design. Travel times also force societal and philosophical re-evaluations. Human multi-generational voyages demand not only technological innovations, but also ethical considerations. How do we sustain purpose and morale across centuries? Should we develop generational ships where successive generations live and die on board, or rely on robotic explorers and remote probes. These questions are deeply intertwined with our conception of exploration itself, emphasizing that interstellar travel is not just a matter of faster ships, but reimagining how missions are planned, managed, and sustained. Communication delays, growing longer with increased distance, are a major challenge. Signals take years to arrive. At 50 light-years, a message takes 50 years. Real-time decision-making becomes impossible, requiring reliance on pre-programmed instructions and onboard autonomous systems. Planning must account for these delays in navigation, scientific operations, and safety protocols. Developing advanced onboard AI to make critical decisions without waiting for Earth's input becomes necessity, not just an option. Logistical planning must also consider long-term power sources, like nuclear reactors or advanced solar collectors capable of functioning over centuries. Spacecraft components will wear out. Maintenance and repair strategies that do not depend on constant resupply are essential. Developing durable, sustainable systems that can operate continually over extended periods is critical for mission success. These phenomena, fundamental physics constraints, interstellar hazards, and immense timescales, force us to think long-term, creatively, and flexibly. They push innovation in propulsion, life support, communication, and autonomous systems. They also prompt us to adjust expectations, recognizing that interstellar exploration is not just about building faster ships, but rethinking how we plan, manage, and sustain these missions across centuries. While these challenges underscore monumental hurdles, they also serve as motivators. They inspire the pursuit of breakthrough technologies and new solutions. Planning for interstellar missions isn't about reaching stars within a decade, but preparing for a journey spanning generations, demanding patience, resilience, and shared vision. Reaching beyond our cosmic neighborhood will require overcoming obstacles that test our ingenuity and resolve. In sum, these phenomena set boundaries, but also inspire innovation. They highlight the need for resilient systems, adaptable strategies, and a long-term perspective. As we face the realities of interstellar travel, our approaches must evolve, embracing automation, resourcefulness, and philosophical shifts, focused on the goal of reaching other worlds despite the formidable challenges. Traveling at or near the speed of light sounds like the ultimate sci-fi dream, but it's riddled with paradoxes and deep scientific puzzles that challenge our understanding of reality. Pushing toward these limits confronts us with questions that stretch the very fabric of physics and philosophy, revealing how intricate the universe's rules are. One of the most well-known issues is the twin paradox. Imagine two twins. One stays on Earth, while the other embarks on a spaceship traveling close to light speed. When the traveling twin returns, they would be younger than the one on Earth. This isn't just a parable. It's a consequence of how time works differently for observers moving at high velocities. The paradox seems to suggest a contradiction. How can both twins be right? But it's resolved by understanding that the traveling twin undergoes acceleration, breaking symmetry, and emphasizing that time dilation depends on acceleration and inertial frames. Still, it underscores a key issue. Under relativistic conditions, time warps and twists, making predictions about cosmic timelines tricky and raising questions about causality and the nature of cause and effect. Then there's the light speed barrier, a fundamental hurdle. According to special relativity, as an object accelerates closer to light speed, its relativistic mass increases without bound, requiring infinite energy to reach exactly that speed. This isn't just an engineering nightmare, it's a core principle of the universe. It prevents objects with mass from breaking the cosmic speed limit and suggests faster-than-light travel may be fundamentally impossible. This creates a conundrum. If no mass-bearing object can reach or exceed light speed, how could three-dimensional travel to distant stars ever be feasible? Are warp drives or superluminal methods utopian fantasies? Or can physics find loopholes to bypass these constraints? The idea of a warp bubble. A space distortion introduces its own paradoxes. Proposed by physicist Miguel Alcubierre, it involves compressing space in front of a spacecraft and expanding it behind, enabling faster-than-light travel without locally breaking the speed limit. But this concept isn't without mysteries. It would require exotic matter or negative energy density, substances yet to be discovered and possibly non-existent in the needed quantities. Further, some physicists question if creating such a bubble might cause causality violations, like signals arriving before they were sent, potentially leading to time travel paradoxes. Time travel, deeply tied to relativistic effects, raises thorny questions. If faster-than-light travel is possible, it could enable closed time-like curves, journeys into the past. This opens paradoxes like the grandfather paradox, where a traveler could prevent their own existence by altering past events. Some interpretations of quantum mechanics and relativity suggest the universe may have self-correcting mechanisms to prevent such paradoxes. Yet, the possibility remains unsettling. Could the universe be protected against these breaches? Do we need new physics to solve this conundrum? The energy requirements are another significant barrier. Accelerating a spaceship to even moderate fractions of light speed demands staggering energy, often millions or billions of times more than current humanity can produce. For example, powering a modest spacecraft might require a significant share of Earth's total energy for years. This makes even hypothetical propulsion methods like antimatter or fusion engines practically impossible with current technology. It also prompts questions about whether new physics or revolutionary energy sources are necessary to overcome these barriers. Relativistic travel also causes differential aging. If a spacecraft could reach near light speeds, the universe outside would age much faster than the crew experiences. While the crew might only age decades, billions of years could pass in the cosmos, after which the universe might have changed drastically. This complicates long-term interstellar colonization, as stars burn out and galaxies drift apart. These effects force us to confront not just engineering challenges, but also philosophical questions about existence, persistence, and our place in cosmic history. Radiation exposure presents another serious issue. Approaching light speed exposes travelers to intense cosmic rays and energetic particles. Even with shielding, high-energy particles could be lethal over long journeys. Our biological understanding shows that prolonged radiation exposure is dangerous, adding medical and engineering challenges to the list of relativistic travel obstacles. In essence, relativistic travel is more than just faster engines. It's an intricate dance with fundamental physics. Each theoretical advance uncovers more paradoxes and constraints, prompting us to ask whether these are inherent limits or stepping stones to breakthroughs. At its core, the universe appears finely tuned, with built-in barriers shaping reality itself. Whether we eventually find ways to bypass these limits or accept them as ultimate boundaries, addressing the paradoxes of relativistic travel pushes science toward its most profound frontiers. When considering the vast distances between stars in the Milky Way, the differences in travel times between human missions and robotic probes become staggering, revealing the technological challenges and strategic considerations shaping our cosmic ambitions. Journeying to Proxima Centauri, the nearest star system about 4.25 light-years away, highlights these differences. Robotic probes utilizing advanced propulsion, like laser sails or nuclear engines, could reach the system in decades or a century, assuming speeds of about 1% to 10% of light speed. While still extremely long, this time frame is within scientific planning and endurance. These explorers could serve reconnaissance, sample collection, and analysis roles, waiting patiently for data over generations. In contrast, human missions face far greater hurdles. To make a crewed journey feasible within a few centuries, spacecraft would need to approach significant fractions of the speed of light, something currently impossible, but potentially attainable with future breakthroughs. If propulsion, capable of reaching 10% of light speed, were developed, a crew traveling to Proxima Centauri would endure a journey of about 40 years, plus acceleration and deceleration time. Traveling at just 1% of light speed extends the voyage into 400 years, risking crew extinction before arrival. Moreover, physiological and psychological stresses of such long journeys are profound. Radiation exposure, microgravity effects, and the psychological toll from solitude and confinement are obstacles with current scientific limits. This makes human interstellar travel a question not just of propulsion, but of human resilience, biology, and long-term sustainability. The fundamental reason for this timing disparity is propulsion technology and energy availability. Robotic probes can be designed for extremely high velocities, pushing the limits of physics, through light sails powered by Earth lasers, nuclear thermal, or antimatter engines, offering higher efficiencies than chemical rockets. These systems prioritize autonomy, capable of gradual acceleration and long-duration missions, unbound by human life expectancy. Humans, however, require life support systems, living environments, food, water, and radiation protection, which add mass, complicate propulsion, and demand immense energy. Accelerating a crewed vessel to even a modest fraction of light speed would require breakthroughs in energy generation, such as future fusion, antimatter, or even matter-antimatter engines capable of providing the necessary power for relativistic travel. Furthermore, the prolonged travel times challenge their practicality and return on investment. Sending humans to distant stars might take centuries, with no guarantee of seeing home again. This raises questions about whether robotic missions, capable of long-term operation, autonomy, and detailed data collection, might be more prudent, especially given their potential for continuous operation over long durations, or evolving into autonomous exploration. Another factor is mission outcomes. Robotic probes can be equipped with artificial intelligence for decision-making and repairs, enduring the harsh space environment and conducting detailed investigations of alien worlds or signs of life. Human explorers, however, depend on complex support. They are vulnerable to failures in life support, energy, or health, making their missions riskier and harder to sustain logistically. Yet, human missions embody the innate drive for discovery, curiosity, and exploration that initially led us beyond Earth. They symbolize reaching out beyond what is currently possible, providing a tangible presence among the stars. This aspiration stimulates research into concepts like generation ships, cryogenic sleep, and artificial wombs, pushing scientific and imaginative limits. Looking beyond Proxima Centauri to stars like Alpha Centauri A or B, or systems within the Sagittarius arm, timescales grow even more immense. Robotic probes could reach these systems over a few centuries, while human missions would require multiple generations or breakthroughs in biology and physics. This disparity in travel times shapes exploration strategies. Robotic probes act as scouts and scientists, capable of solo, centuries-long journeys gathering data and relaying information back to Earth. Human missions resemble cosmic expeditions, requiring complex logistics, life support systems, and survival mechanisms that are still in development. This divergence highlights both the excitement and humility of space exploration. It underscores how technological innovation, energy mastery, and biological resilience intertwine in our quest to reach the stars. Robotic probes are our current explorers, capable of crossing light years in a human lifetime or less. Human missions remain a distant goal, dependent on advances in physics, engineering, and biology. Looking forward, the interplay of robotic and human exploration will define our journey through the cosmos. Whether through silent, relentless robotic ships or the tentative steps of humans on distant worlds, each path offers insights into the universe's secrets, broadening our understanding of what's possible, forever shifting our view of our place in the universe. When contemplating interstellar travel across the vast galaxy, one of the most critical questions concerns life support, supplies, and sustainability. These are not just logistical issues. They fundamentally determine how long a journey can last beyond our solar system. Traveling toward a star system hundreds or thousands of light years away requires more than propulsion speed. It depends on how well travelers can sustain themselves throughout the voyage. The first vital element is life support systems. Complex setups designed to provide breathable air, potable water, and environments that support mental and physical health. Earth's environment is maintained through an intricate balance of nature and technology. Replicating this on board a spacecraft, especially for multi-generational voyages, demands a self-sustaining ecosystem. Closed-loop life support systems that recycle water and air with minimal loss are essential, as they reduce the need for resupply from Earth. Sending supplies across light years is impractical with current technology. These systems require advanced biological and mechanical processes, bioregenerative life support that employs plants, bacteria, and organisms to process waste and produce fresh air and food. They must be resilient for decades or centuries at sea. The challenge is preventing catastrophic failure over such long periods. Oxygen levels must be carefully managed to avoid hypoxia or hyperoxia, while carbon dioxide must be continuously scrubbed. Crew mental well-being, often overlooked in technical discussions, relies on sufficient recreation, social interaction, and connection to Earth, even if faint. Food supplies present unique challenges. Carrying enough provisions for decades is impractical due to weight constraints. The solution largely involves onboard cultivation, growing crops with hydroponic or aeroponic systems that replenish calories and essential nutrients. Genetic engineering could support fast-growing, nutrient-dense plants optimized for space. Algae or microorganisms might provide protein or oxygen as byproducts. This creates a biological mini-ecosystem, balanced, monitored, and maintained. Every kilogram of onboard grown food reduces dependency on Earth resupply, directly extending mission duration. The more self-sufficient the crew, the longer they can remain without external support. This ecological system forms the backbone of sustainability and directly impacts the feasible length of the journey. Other supplies, medicine, spare parts, personal items, must be produced on board, necessitating advanced manufacturing like 3D printing and robotic fabrication. Crews could produce necessary components on demand, reducing dependence on Earth. A future ship integrated with robotic manufacturing would essentially be a self-sustaining industrial unit capable of repairs and upgrades, extending operational lifespan. Energy is central to these systems. Power must be reliable, abundant, and sustainable over decades. In deep space, solar energy becomes less effective away from the sun, requiring alternative sources such as nuclear fusion or fission reactors. These reactors offer the continuous energy flow needed to sustain life support, grow food, run manufacturing, and maintain ship systems. Reliable, long-lasting power sources greatly extend mission duration by reducing dependence on stored fuels, which would otherwise limit the journey. Such considerations reveal a tight engineering, biological, and energy science interplay. These directly influence how long crew members can live and work in space before resupply or rescue becomes impossible. Every limitation in life support or supply capacity acts as a de facto deadline, unless breakthroughs in recycling, in situ production, or even life extension occur. The psychological aspects are equally important. Longer durations in confined spacecraft environments make mental health a critical concern. Crew morale, social cohesion, and cultural activities require careful management, including creating livable environments, offering recreation, and fostering a sense of purpose. Maintaining mental resilience can extend or shorten the practical duration of the voyage. In essence, the feasibility of interstellar missions hinges on overcoming constraints related to life support and supplies. Air, water, food, energy, and spare parts are all limiting factors, defining how far and how long humanity can travel. It's a race against time, not just in propulsion and physics, but across ecological and biological limits. Achieving self-sustaining ecosystems, regenerative life support, and adaptive manufacturing could push the boundaries of what's possible, transforming the dream of crossing the galaxy into a potential reality, one that could last generations, driven by our capacity to sustain life so far from home. Careful, innovative engineering and biological solutions are key. They will ultimately determine whether humanity can extend its reach into the stars, making interstellar travel not just a distant dream, but an achievable goal. Imagine a future where, instead of waiting centuries for humans to journey across the stars, we send highly autonomous robotic explorers. These emissaries could revolutionize our understanding of distant planets in ways once imagined only in science fiction. What are the implications of deploying these explorers? How might they reshape our approach to interstellar travel, deepen our galaxy knowledge, and influence human space exploration? Sending humans across interstellar distances remains a daunting challenge. The speeds required to reach nearby star systems within a human lifetime are staggering, and logistical hurdles, life support, radiation shielding, psychological well-being, are significant. Autonomous robotic explorers bypass many of these issues. They don't need life support systems or habitats, allowing them to operate independently for decades or even centuries. Their missions can be designed for endurance, with sophisticated AI managing navigation, data collection, and decision-making autonomously. Their autonomy means they can venture into poorly understood and unpredictable galaxy regions. They can make real-time decisions when encountering unexpected phenomena, such as unusual planetary atmospheres, novel mineral compositions, or strange electromagnetic signatures. Unlike pre-programmed probes following a fixed course, autonomous explorers adapt their mission plans dynamically, seeking out scientifically interesting features. This flexibility amplifies scientific returns exponentially, opening windows into otherwise inaccessible galaxy regions due to communication delays and vast distances. Advances in artificial intelligence enable these explorers to learn from their environment, identify signs of life, past or present, and prioritize tasks based on scientific value. They might discover biosignatures on planets where we least expect life, or detect subtle clues about planetary system histories. They become intelligent, self-directed agents dedicated to gathering knowledge and transmitting it back to Earth or other command centers, fundamentally transforming cosmic exploration. Another significant implication involves resource utilization and in situ analysis. Equipped with advanced instruments, autonomous explorers can analyze mineral compositions, atmospheric samples, or potential biological materials. They serve as scouts, assessing whether a planet or moon is suitable for future human settlement or resource extraction. Such reconnaissance is crucial for decision-making, identifying water ice deposits, mineral-rich sites, or optimal locations for establishing bases, all ahead of human arrival. Furthermore, these explorers could pave the way for interstellar diplomacy as they gather information and potentially detect signs of extraterrestrial life or civilizations. Implications extend beyond pure science. They become ambassadors of humanity's curiosity and technological prowess. Their data might influence planetary protection policies, international agreements, or spark public interest in space exploration. Deploying autonomous robotic explorers also raises profound ethical and philosophical questions. How do we ensure their actions do not inadvertently harm potential ecosystems or disrupt unknown habitats? What protocols should govern their behavior, especially if they encounter extraterrestrial life? These questions gain importance as technological capabilities advance, necessitating careful consideration of the risks involved. From a logistical standpoint, robotic explorers offer a cost-effective approach. Sending robotic missions is generally cheaper and safer. You don't need life support, safety protocols, or rescue plans, reducing risks significantly. This cost efficiency makes interstellar missions more feasible economically, encouraging governments, private enterprises, and international collaborations to invest heavily in robotic exploration initiatives. Looking into the future, these explorers might evolve into autonomous colonies or mining stations once they identify resource-rich planets. Imagine self-sustaining fleets harvesting minerals, producing energy, and building infrastructure autonomously. Such developments could mark the birth of a galactic civilization, expanding outward, with robots acting as initial explorers and settlers, paving the way for human pioneers to follow. However, reliance on autonomous exploration might diminish the urgency of developing human travel capabilities. If robots can learn so much, will there be enough motivation to overcome the immense challenges of interstellar human travel? Or will robotic explorers serve as scouts, handling the risky, time-consuming explorations, leaving humans with the easier task of arriving after robots have laid the groundwork? Ultimately, autonomous robotic explorers hold promise, not only for expanding knowledge, but also for transforming the entire paradigm of cosmic exploration. They operate beyond current physical and technological limitations, becoming the vanguard of humanity's quest to understand the universe. They could unlock secrets of distant worlds, identify new habitats, and discover signs of life, all without the constraints that hinder human missions. As technology progresses, these explorers will become our most valuable tools for unraveling galaxy mysteries, guiding humanity into a new era of cosmic discovery. Imagine a future where humanity transcends conventional physics and engineering, where breakthroughs fundamentally reshape interstellar travel. Today, the vast distances across the Milky Way, billions of miles between stars, serve as formidable barriers, making even our fastest spacecraft, like the Parker Solar Probe, take thousands of years to reach the nearest stars. But what if future innovations could dramatically alter these timeframes? Consider propulsion systems that surpass existing chemical rockets. Envision antimatter engines, which utilize the immense energy released when antimatter particles annihilate with matter. Because antimatter reactions are nearly 100% efficient, converting mass directly into energy, such engines could propel spacecraft at a significant fraction of the speed of light. A spacecraft powered by antimatter annihilation might reach Alpha Centauri in just decades or less, reducing travel time from thousands of years to human lifetimes. Although producing, storing, and controlling antimatter remains challenging, advances in particle physics and containment tech could make antimatter propulsion feasible. Beyond antimatter, laser or light sail propulsion systems could revolutionize journeys. Ground-based lasers could accelerate ultralight spacecraft with reflective sails, an idea exemplified by projects like Breakthrough Starshot. If perfected, these laser-driven sails could reach relativistic speeds, approaching a significant fraction of light speed. Such velocities could enable reaching nearest stars within a few years to decades. Deploying fleets of tiny, inexpensive probes powered by light sails would exponentially boost exploration capacity, transmitting data back and paving the way for future crewed missions. In the realm of theoretical physics, ideas like warp drives could fundamentally alter travel. If future research confirms practical manipulation of spacetime, creating a warp bubble that contracts spacetime in front and expands it behind, spaceships could effectively ride these distortions, moving faster than light without violating Einstein's laws. Such warp drives, based on concepts like the Alcubierre metric, could make interstellar travel feel instantaneous, with voyages to neighboring stars taking only days or weeks from travelers' perspectives. Though current concepts depend on exotic matter and energy with unknown properties, ongoing studies into spacetime manipulation and negative energy might someday make them feasible. Advances in energy production will also be crucial. The enormous energy requirements for near-light-speed travel, or warp systems, necessitate breakthroughs in harnessing and storing power. Future civilizations might develop fusion reactors, capable of sustained enormous outputs, or tap into still theoretical sources like quantum fields, dark energy, or zero-point energy. These technologies could provide the immense power needed to propel ships at relativistic speeds, making journeys previously impossible achievable within human lifespans. More efficient energy sources would also reduce costs and risks associated with long interstellar trips. Biotechnology and resilience engineering could indirectly affect travel time by enhancing human longevity, health, and survivability during extended missions. If humans or their artificial descendants develop methods to dramatically extend lifespan or create self-sustaining life support systems, crews could survive decades or even centuries on voyages without ultra-fast propulsion. This approach would reduce dependence on pushing current propulsion boundaries, instead focusing on making long-duration space travel safe, sustainable, and manageable. Long-term genetic modifications, regenerative medicine, or cybernetic augmentation could eventually allow explorers to endure the rigors of interstellar journeys comfortably. International collaboration and global research initiatives will likely accelerate technological progress. Pooling resources, talent, and data will foster breakthroughs in materials, science, nanotechnology, artificial intelligence, and robotics. Advances in nanomaterials could yield ultra-light, durable spacecraft components, reducing mass and increasing acceleration efficiency. Artificial intelligence could optimize navigation, propulsion, and life support, handling complexities of long missions with minimal oversight. Autonomous systems could repair and maintain spacecraft, during decades-long journeys, reducing the need for constant human intervention. However, every leap in technology introduces challenges and risks. The colossal energy demands of near-light speed travel, or space-time manipulation, could stretch our understanding of physics and necessitate novel energy harnessing methods. Navigating interstellar space exposes hazards such as radiation, micrometeoroids, and dense dust clouds, demanding revolutionary shielding, perhaps electromagnetic fields or advanced composite materials. Ethical concerns about manipulating space-time or creating properties like negative energy must be addressed to ensure responsible development. Future breakthroughs might include controlling gravity or creating artificial wormholes, potentially enabling instant traversable shortcuts through space-time. If practical, these could reduce travel times from thousands of years to moments, shrinking the universe and facilitating rapid exploration, colonization, and resource extraction. Each technological leap, be it advanced propulsion, energy harvesting, space-time manipulation, or life extension, has the potential to transform interstellar travel from an impossibility to routine. The timelines for reaching nearby stars could shorten from millennia to decades or days, making the universe more accessible and less an unreachable frontier. Scientific innovation, creativity, and exploration suggest that what now seems science fiction could someday become humanity's everyday reality, expanding our cosmic horizons. Embarking on interstellar journeys involves significant scientific, engineering, and ethical challenges. These layers must be understood to grasp the scope of the undertaking. Scientifically, one foremost obstacle is the vast distances involved. Alpha Centauri is over 4 light-years away. Even with advanced propulsion, fusion engines, or antimatter drives, travel could take decades or centuries. Our current physics limits us, requiring breakthroughs in manipulating space-time or achieving near-light speed velocities. Reaching stars within a human lifetime introduces relativistic effects, complicating navigation and communication. Time dilation means travelers experience less time than observers, raising questions about synchronization and managing generations crossing vast spans. Prolonged space travel also raises biological and health issues. Microgravity and cosmic radiation can harm health, impair cognition, and threaten crew survival. Developing effective shielding and life support systems for decades or centuries is crucial. Genetic and biomedical enhancements might mitigate some problems, but they open ethical debates about human modification and control. Engineering challenges are immense. Current chemical rockets are unsuitable for interstellar speeds. Fusion propulsion remains experimental, while antimatter drives offer promise, but pose production, storage, and safety issues. Materials must withstand radiation, heat, and particle impacts at relativistic speeds, demanding innovations in nanomaterials, superconductors, and radiation shielding. Power sources are vital. Efficient, durable, compact energy sources are needed to sustain interstellar spacecraft. Concepts like laser sails depend on powerful ground lasers, requiring precise aiming, large-scale laser arrays, and stability over light years. Autonomous systems and AI must manage these journeys, making real-time decisions, repairing, and adapting to unforeseen challenges. Developing fail-proof AI capable of ethical decision-making adds complexity, especially if life and death choices are involved. Ethically, many issues emerge. Sending humans necessitates weighing acceptable risks, psychological strains, and health consequences. Questions of consent and moral responsibility arise. Are we justified in risking lives for distant exploration? Additionally, ethical concerns about disturbing extraterrestrial environments or introducing Earth microbes to pristine worlds are prominent. Do we have the right to interfere with or exploit potential alien biospheres? Resource allocation presents challenges too. Investing trillions of dollars in interstellar travel must be justified against pressing issues like climate change, poverty, and health crisis. Is it ethical to divert significant resources to space endeavors when immediate terrestrial needs remain urgent? This raises questions about priorities and morality in resource management. Governance and geopolitics add further complexity. Who controls these missions? How can equitable access to discoveries, benefits, and colonization be ensured? There's a risk that powerful nations dominate, potentially leading to new forms of cosmic colonialism. International agreements, akin to treaties on the Moon or Antarctica, are necessary but difficult to establish amidst competing interests. The discovery of extraterrestrial life amplifies ethical responsibilities. We'd need protocols to prevent contamination and manage data sharing. Do we have moral obligations to protect other biospheres? What rights do these worlds have? Can we resource them or establish colonies, risking environmental alteration? Multi-generational missions pose unique ethical dilemmas. They could span centuries, requiring multiple generations or autonomous succession planning. How do we preserve identity, culture, and purpose across so long a span? Do we owe future explorers a meaningful mission? Or are we merely planting seeds in space without guaranteeing their well-being? Psychological and social issues are critical. Long isolation and confinement could weigh heavily on crew members. Developing resilient mental health support, social cohesion strategies, and tools like virtual reality will be essential. Is it right to subject humans to such conditions? Balancing safety, moral responsibility, and the human spirit's drive to explore is complex. In sum, interstellar travel isn't solely a scientific or engineering challenge, but a profound ethical one. It tests our values, responsibilities, and future visions. Every scientific breakthrough must be evaluated morally, ensuring exploration aligns with wisdom and respect for ethical stakes. Our pursuit of the stars should be guided by curiosity and progress, tempered by moral sense and caution. This journey involves respecting the environment, safeguarding human dignity, and contemplating our role as explorers in the cosmos. As we strive forward, we must navigate these ethical waters carefully, recognizing that our decisions will shape not only our destiny among the stars, but also our moral legacy here on Earth. Energy requirements fundamentally shape the feasibility of interstellar journeys by defining the practical limits of propulsion, mission duration, and sustainability. The immense distances within the Milky Way, measured in light years, demand advances in propulsion technology and energy generation far beyond current capabilities. To reach even the closest stars within a human lifespan requires technology capable of propelling spacecraft at a significant fraction of the speed of light, involving staggering energy consumption and management challenges. Currently, chemical rockets are insufficient for interstellar travel due to their low energy density and limited thrust. Their fuel mass increases prohibitively with velocity, making rapid transit impossible. Achieving 20% of light speed would require energy amounts surpassing humanity's global energy production over centuries, rendering chemical propulsion impractical. This pushes us toward exploring advanced propulsion concepts, each with distinct energy demands and technological hurdles. Fusion propulsion appears promising, leveraging reactions similar to those powering stars. Fusion engines could, in principle, provide continuous and efficient thrust, utilizing abundant isotopes like deuterium and tritium. The main challenge is achieving controlled, sustained fusion reactions within compact, spacecraft-compatible reactors, an active research area. Fusion offers higher energy efficiency than chemical fuels, but scaling it up for interstellar missions demands breakthroughs in plasma physics, reactor design, and materials capable of withstanding intense conditions. The immense energy needed for fusion reactions also requires powerful onboard energy sources and reliable methods to produce and sustain fusion in space. Antimatter propulsion offers even higher efficiency. When matter and antimatter annihilate, they release energy in accordance with Einstein's ERMC2, enabling potentially relativistic velocities with less fuel. A tiny amount of antimatter could, theoretically, power a spacecraft to a significant fraction of the speed of light. However, producing and storing antimatter is extraordinarily energy-intensive. Current methods require more energy input than the antimatter yields, making large-scale production impractical. Secure and safe storage over extended missions presents considerable challenges, preventing accidental annihilation and managing radiation hazards. Laser sail propulsion provides an alternative approach, using a powerful ground or space-based laser beam to propel a highly reflective sail attached to the spacecraft. This method could accelerate ships to relativistic speeds without carrying large fuel quantities. The primary energy requirement involves generating and directing a focused, high-power laser beam over enormous distances without losing coherence or intensity. Achieving this requires advanced laser technology, adaptive optics, and ultra-precise aiming, pushing current engineering capabilities. The sail's materials must endure intense laser radiation and thermal stress during acceleration. Beyond propulsion, energy requirements encompass life support, scientific instruments, and onboard systems across multi-decade or multi-century missions. For multi-generational ships, sustainability depends on efficient energy storage, recycling, and potentially in-situ resource utilization, ISRU. ISRU involves harvesting local, celestial, or interstellar resources, such as hydrogen, water, or minerals, to produce fuels, breathable air, and power, reducing reliance on initial supplies. This adds energy demands for extraction, refinement, and storage, increasing mission complexity, but being vital for long-term survival. Powering these systems sustainably also involves addressing energy density. Nuclear fission and radioisotope thermoelectric generators currently power long-term missions within the solar system. However, these sources are inadequate for interstellar endeavors, especially those involving relativistic speeds. Fusion or advanced nuclear reactors could provide reliable high-output energy, but require extensive development, including materials capable of withstanding high radiation and thermal loads. The societal and economic dimensions of energy requirements are profound. Developing the vast energy infrastructure needed would necessitate unprecedented global cooperation, technological innovation, and resource allocation. Building capacity to generate, manage, and safely utilize energies at such scales could transform humanity's energy landscape, perhaps advancing renewable energy, fusion, or space-based solar power. Ultimately, energy is the core limiting factor in realizing interstellar travel. Without breakthroughs in efficient energy harvesting, generation, storage, and safety, such journeys remain theoretical. Achieving relativistic speeds or even significant fractions thereof demands new propulsion technologies and revolutionary energy science advancements. These solutions will shape the future of human space exploration, turning today's impossibilities into future milestones. The pursuit of interstellar exploration depends on mastering cosmic-scale energy, making it the most critical challenge and perhaps the greatest opportunity facing humanity's future beyond our solar system. To bring the dream of reaching other planets in the Milky Way closer to reality, scientists and engineers are exploring innovative solutions that could one day turn science fiction into science fact. The road ahead isn't straightforward, but promising pathways exist that could push the boundaries of what we currently deem achievable. One foundational solution involves developing advanced propulsion systems. Conventional chemical rockets, reliable for short missions within our solar system, won't suffice for star systems hundreds or thousands of light years away. To make interstellar travel feasible, propulsion technology must leap forward dramatically. Fusion drives are among the most promising candidates. Unlike current fission reactors or chemical engines, fusion engines harness the process powering the sun. Mastering controlled nuclear fusion in a compact, efficient way could propel spacecraft to velocities near the speed of light, drastically reducing travel times from tens of thousands of years to a few decades or less. This requires breakthroughs in plasma confinement, materials enduring extreme temperatures, and sustainable energy sources. Antimatter propulsion offers another exciting pathway. When antimatter annihilates with matter, it produces enormous energy per Einstein's e-mc2. If we can safely produce, store, and harness antimatter, engines could operate at unrivaled efficiencies, enabling spacecraft to accelerate to near-light speeds. However, antimatter production is currently inefficient and expensive, and containment poses challenges because it annihilates upon contact with matter. Overcoming these hurdles could revolutionize interstellar travel, making journeys that currently take generations possible within a human lifetime. Beyond propulsion, concepts like warp drives and wormholes offer transformative potential. Rooted in Einstein's general relativity, these ideas suggest manipulating space-time itself, creating a bubble that compresses space ahead and expands it behind, enabling faster-than-light travel without violating physical laws. While speculative and facing technical and theoretical challenges, ongoing research into exotic matter and space-time topology fuels hope that someday these solutions will be feasible. Laser sail technology presents another pathway that's more immediately attainable. Imagine a spacecraft with a lightweight reflective sail propelled by high-powered lasers on Earth or in orbit. Photons transfer momentum to the sail, providing continuous acceleration. This approach could reach a significant fraction of light speed over decades, and because it relies on external energy rather than onboard fuel, it offers scalability for interstellar probes. Projects like Breakthrough Starshot are already exploring this concept, aiming to send tiny spacecraft to neighboring stars within a human lifetime. Technological innovation must be complemented by breakthroughs in energy sources. Achieving the immense energy demands for advanced propulsion requires cleaner, more efficient, and abundant energy supplies. Fusion energy, if perfected, could serve as a cornerstone. Space-based solar power stations could beam energy via microwave or laser transmission to spacecraft, ensuring continuous power during long journeys. Materials science is another critical pathway. Long-duration missions expose ships to cosmic rays, micrometeoroids, and deep space conditions. Developing materials that are strong and lightweight is essential to protect inhabitants and equipment. Advances in nanomaterials, self-healing materials, and radiation shielding could significantly improve vessel survivability and longevity, making multi-decade or multi-century missions feasible. Artificial intelligence, AI, also plays a vital role. As ships venture into unknown territory, autonomous systems must navigate, repair, and adapt without constant human intervention. AI could enable complex problem-solving, scientific analysis, and decision-making, especially as communication delays with Earth could span years. This autonomy reduces crew requirements and simplifies rescue or repair missions, making long journeys more efficient and resource-effective. Resource sustainability, addressed through in-situ resource utilization, is crucial. Instead of relying solely on Earth-supplied provisions, future spacecraft could harvest resources from asteroids, planets, or moons along the way. Extracting water, minerals, and building materials from local sources would reduce payload weight and dependence on Earth. This approach could sustain multi-generational missions and establish outposts or colonies in star systems. Addressing societal and philosophical challenges is equally essential. Developing life support systems capable of sustaining humans over decades requires not only technological solutions, but also understanding psychological and social needs. Creating closed-loop ecologies, fostering community cohesion, and supporting mental health are critical for long-term space habitation. International collaboration and shared visions can accelerate progress. Building infrastructure, conducting research, and sharing knowledge across nations are vital. Just as the international effort behind the International Space Station has demonstrated, pooling resources and expertise can overcome enormous scientific and technical challenges. Each of these pathways forms part of a comprehensive puzzle. No single solution alone will make